já ganhou um livro desse Making Glass Better. Você tem esse livro?
Que versões há? Há mais do que uma versão? Ou só existe só um? Havia uma update?
Eu não sei se tem update, não.
Deixa eu me dar uma olhada e eu posso dizer. Eu tenho um.
Se você tem, aí deixa, porque eu só tenho mais dois aqui. Esse aqui. Tenth Anniversary.
Eu acho que
Summer School.
Creio que eu tenho.
Você tem, né?
Uhum.
Então tá bom. Então vamos deixar para outro.
Sim, tranquilo.
Tá, obrigado. Você que me pediu um livro para o seu orientador? Foi você que me pediu um livro para dar para o seu orientador? Não foi? Não, não. Tá, uma moça que estava aqui. Que o orientador dela chama Alisson. Mas eu guardei. Oi.
Tem desses sobrando?
Então, tem só dois sobrando, tem um professor que não ganhou ainda. Se esse professor que não ganhou já tem, porque algumas pessoas já têm, aí você está na fila.
Eu mostrei para ele, ele queria...
Quem fizer a melhor pergunta.
Tem que fazer boas perguntas.
Fazer uma pergunta. E eles vão ver se é boa ou não. Quem fizer pergunta.
Não tem chance, né?
Exatamente. Okay, it's 13:44. I'm using now the German approach. 10:45 now. It's my distinct pleasure and honor to introduce Professor Sundaram from Alfred, also from the Alfred team, who will be speaking about a kind of unique approach to understand glass in general, right? Not many people work in this particular topic.
Maybe after this lecture, more people will work.
Exactly. So, Professor Sundaram, thank you so much.
Thank you for the invitation. Just wanted to check, can you hear me all right? There's no echo? Thank you. I thought I would start with a question. How many of you heard about terahertz waves? Oh, okay, that's good. And does anyone think you've been exposed to terahertz waves today? Yes or no? You think so? Okay, any other answers? Sorry? Could you repeat that, please, maybe? Yes, yeah, okay. I have been exposed to terahertz waves, and as I'm speaking, I am getting a little bit terahertz waves, okay? So where from it comes? From a cosmic radiation, okay? How many of you think you've been gamma irradiated? Gamma radiation. It's one of the nuclear. Do you think you've gotten gamma?
I hope not.
But
Or we are getting a little bit.
If you've taken a plane to come here, you've been gamma irradiated, teeny bit, okay? All right, but a very, very low dose, okay? About radiation, it's always the dose is more important. Whether you're exposed to it or not, how much you've been exposed to.
So even here indoors, we are getting some gamma.
Yeah, in fact, if you're a frequent flyer, platinum card holder, you've been exposed to more gamma radiation than others who are not traveling much. Okay, anyway, leaving the radiation side, trust me, there is a connection here. I thought I would first tell you how I ended up in terahertz waves, because I just got all my education in ceramic engineering, traditional glass and ceramics, and material science. By the time I was doing my PhD, it was sort of material science, but I was still doing ceramics and glass. And initially, I was really studying regular properties, viscosity and everything. The way I got exposed to long wavelength is I was working in Pacific Northwest National Lab. Before I came to university as a professor in 2011, I was working on a lot of unique projects. One of the projects is highly complex borosilicate glass melt. They are simulated nuclear waste. Can you measure their properties without ever touching it. You can't touch it, okay? All right. So one of the projects I had was we just borrowed and whatever diagnostic tools the fusion community was using, nuclear fusion community, and guess what? They were using millimeter waves. This is a part of the electromagnetic spectrum I'm going to show you. They were using that portion of electromagnetic radiation to use that to detect temperature of fusion, surface conditions, all those things. So we borrowed that technique because I had a collaborator at MIT Fusion Center. So we were using gigahertz millimeter waves to probe glass melt, glass surfaces, and we were able to measure viscosity, compositional variation, any bubbling happening, those kind of things. Okay, so I kept working on gigahertz, the millimeter waves, and when I moved to Alfred, one of the things I was thinking is I want to see what is out there. I don't want to do the same projects I did in National Lab, so I was interested in terahertz waves. I was curious what it is. So that's how I got in. But let me start my presentation. In the presentation, hopefully you will get all your answers. And please feel free to ask me anytime. And hopefully that will give you something new to learn and maybe something interesting, okay? Glass is an exciting state of matter. There's plenty of room for all sorts of science and techniques. With that, my talk is going to be, this is a brief overview. I'm going to quickly tell you what is terahertz waves, how they are emitted, and why should we be interested in terahertz waves, particularly in glass science. And I'll talk a little bit of glass science related to terahertz waves. So I'm going to call that terahertz glass science, if you don't mind. And I'm going to then present some of our results. I will select very small portion of my results to maintain the time I'm allotted to. I do want to complete on time. I don't want to cut into Dr. Malton's time. Then I will give you some quick conclusions about what it's all about, okay? This is an electromagnetic spectrum, and sorry, it's a little cluttered, but you probably guessed this is the electromagnetic spectrum for terahertz people, terahertz community, okay? The reason I say that is the 1 terahertz is right at the middle of this diagram, 1 terahertz. The good thing about this chart is it gives you frequency, wavelength, EV, energy, all in the same scale. You can see all of them in the same scale. And at the top, you see the dimensions and wavelengths. So if you look at 1 terahertz right here, it's about sub-millimeter dimension we are talking about. And unless you are doing reflection, other type of measurements, you are probing sub-millimeter portion of your samples. So it's not atomic scale. It's not interatomic spacing scale, okay? So if you see below, there are many, many applications. A couple of things I want to point out to you. There is another unique thing about terahertz waves is it connects. It's actually called terahertz bridge in the terahertz community because it connects to the right of the terahertz, to the left of the terahertz. You see all the familiar areas, infrared, ultraviolet, and at the thin slice you see is the visible spectrum, and you have X-rays. So this side, we are really talking about ionic contributions, ionic polarization, and a lot of phenomena arises from ions and optics. And if you are looking at this side of the terahertz, for the 1 terahertz, you're looking at all electronics, okay? So it turns out at around 1 terahertz, optics meets electronics. So that means if you're purely looking at optical phenomena, you use all the spectroscopic techniques, you're familiar with it. And if you use purely electronic spectra, you all this technique. But terahertz wavelength gives you both contribution you can measure. So that's the biggest advantage, okay? Typically, when I say terahertz, I'm talking about 0.3 to terahertz. Sorry. This shows great promise for a lot of scientific phenomena. And some examples I'm going to give you. One is the electrons in highly excited atomic Rydberg states you might have heard about in your chemistry class. They actually orbit and small molecules rotate at terahertz frequencies. So if you want to see them, you can go to terahertz frequency, you can see them rotate. You can measure the resonance. Electrons resonate at the terahertz frequencies in semiconductors. So you can study Courier dynamics, ceramic or glass semiconductor material. And also, do you think this surface emits terahertz radiation? Actually, yes, a little bit, because any black body, about 10K, it does radiate some terahertz waves, because remember, black body radiation has a wide distribution of wavelength, but one of the dominant wavelength is gigahertz and terahertz waves, okay? So they are present all the time. So remember when I told you I did use gigahertz techniques to look at glass melt, guess what? I didn't generate gigahertz radiation to shine on the sample. The hot melt already produced black body emission radiation. It already was producing a part of gigahertz, okay? All right, so another interesting thing is over a period of time, there are spectroscopic and imaging equipments have been developed by companies. You can buy them. They are maybe $500,000 now, and they keep improving, but they're still cost prohibitive a little bit. But there are many out there right now. When I started, there were a few. Now there are a few more now. So where does the terahertz emission come from? You may wonder. When I say optical photon, that visible, the light you see, your transparent glass, whenever we're talking about optical photonics, the radiation actually comes from tightly bound electrons. So because of that, we are talking about discretely quantized energy, and closer to the core of the atom you go, higher the energy you will need to emit the radiation, optical photon. So if you're talking about radio photon, everything electronics you're talking about, in this case, the loosely bound electrons are jumping between the outer electron shells. That is what is we call radio emission, radio waves. Terahertz photon, it's something nicely in between these two energy ranges. So they are unbound electrons oscillating within a magnetic field or in a laser field. If you apply that, you can produce terahertz waves, okay? Another interesting thing is terahertz waves can propagate in free space, in air. It can propagate with the less loss. As you know, optical photon, the light, laser light, if I try to transmit in free space, it's going to lose a lot of energy because it scatters because of its wavelength and interaction with the particles, anything in the free space. That doesn't happen to terahertz waves because they are long wavelength. They don't interact with the dust or anything on its way. So that means you can emit and transport terahertz waves in free space or through a material as well. And if you look at the terahertz waves, they show up in many, many scientific fields. I'm just giving only a few examples. You can see some of you can look for singly ionized nitrogen and carbon monoxide signature in the galactic formation. Those species have terahertz signature. Okay? So there are telescopes who are looking at and recording those terahertz signature from those singly ionized atoms in the galaxy. There are several pollutants and nerve gas, those kind of things. They do have signature in terahertz waves, so you can use that to sense those chemicals, those obnoxious things, those threats. In medical field, terahertz waves are being applied. Several biomolecules and tissues have specific terahertz signature. So just to give you an example, the company which sold the terahertz spectrometer to me, TeraView in England. 2 years ago, they have launched a product for scanning breast cancer, because the breast cancer tissue has a specific terahertz signature, so they can scan and see, and it's a non-ionizing radiation. So terahertz waves are non-ionizing. So if I get exposed to some terahertz wave, big deal. Okay, X-ray, no. Just to give you an example, there are plenty of applications in national security. There are several contrabands have terahertz signature. Whenever you come across large organic molecules, proteins, they all have unique terahertz signature because they can rotate, they can freely move around. That's what leads to a terahertz resonance happening in those frequencies. So you can use them to detect passively. You can also detect actively. You can use terahertz and gigahertz waves. This is used in military. It's called active denial system. So you can send a strong terahertz beam towards a system or a person. You can jam electronics. You can decapacitate a person. The last one is a wireless application for very fast personal wireless transmission. You can use the terahertz windows. Right now, it's not being used for commercial purposes, but when they open up, you will be able to access those frequencies for local communication. All right, so what is the glass science? Because all this is great, but why do I care if I'm working on glass? How many of you heard about boson peak? Yep, it's a common term in glass. It's a characteristic frequency you see. This is a peak you see, as the name says. The boson peak typically lies in the terahertz range. We know that. That's all we know. And there have been a lot of research in the past done by physicists and electronic materials research groups. And, but we know several empirical things now. What we know is the intensity of boson peak is related to how strong the glass is. Okay? The stronger the boson peak intensity, strong is the glass. And if it's weak, it's fragile, okay? But where from the boson peak comes up, the origin of boson peak is a very exciting topic. It's still being researched, but almost entirely in physics community. And some glass community have been also making measurements. For various reasons, it's kind of hard to measure a boson peak. They don't show up easily. We know they exist, but it's hard to find. Some of the techniques researchers have used are inelastic neutron scattering, Raman scattering, far infrared spectroscopy, and terahertz time domain spectroscopy. I'm mainly going to talk about the terahertz time domain spectroscopy, but I wanted to give you a little bit of flavor for the glass science. This is a fantastic group of papers published by Professor Greaves. You can see this is published all between 2003 and 2011. And what the group did is they took zeolite crystal. It has got a cage-like structure with a lot of gap cages within the structure. They took zeolite and then they slowly collapsed the crystal. They applied pressure and temperature and collapsed until it is completely amorphized. It became 100% glass, okay? And while they were doing, this group was using a specific technique, which is inelastic neutron scattering, to track what is happening to the cage structure. And there's an alpha cage, there's a beta cage, and other features in the structure, in the crystal structure, how you are slowly losing them, and finally you completely lost them, and you get boson peak. Okay? So that means when your crystal structure species are collapsing, you finally end up getting a boson peak. But remember, this curve is about 90% already amorphized. you still see the alpha cage and beta cage, some of these features. And these cages respond in the terahertz bands. So they tracked terahertz bands at 4.5 and 9 MeV using the neutron scattering technique. So they could literally see a crystal transitioning into glass. Okay? So this gives a couple of ideas for you. So if you want to study glass transition or even relaxation back, you may want to start with a crystal, maybe of geological interest. I'm thinking of Dr. Moulton here. Yes. And you can use temperature and pressure to gradually convert that into amorphous glass, and then you may be able to literally watch boson peak up here. Okay? Another idea here is we don't know what actually is inside this boson peak. You just see a large peak, and even if you detect it, if you find it, from this diagram, you probably know the shape of the peak. They all came from the distinct bands present in the crystal. So obviously, there are signatures of the crystal bands still present in this glassy state, okay? So anyway, so Professor Greaves, I'm quoting from Professor Greaves' paper. Broadly speaking, terahertz vibrations drive the dynamics of glass formation and phase transformation. So this is a strong statement, and then you're wondering, how come terahertz spectroscopy is not so common in glass community, okay? It is just a question of, number one, trying, and another problem is terahertz spectroscopy and some of these techniques are predominantly developed by electrical engineering and physics community, so it takes time to cross over to materials community and glass community. But now I can say there are a few groups measuring some of these techniques. Okay. Anyway, another science I want to point out before I move on is there was a question yesterday about the shape of the relaxation curve. I think there was a question from you. What happens above certain frequency? What happens to the epsilon double prime? So you may not have heard about this. How many of you heard about Lunkenheimer-Lloyd plots? Anybody heard about it? Okay, it's a very interesting plot. This is Lunkenheimer and Lloyd plots. It's schematically shown for two different temperatures. And if you look at the frequency scale, here it's about 10 to the power 15. It is 10 to the power minus 6. We are talking about over 15 or 18 orders of magnitude of frequency. And these are various relaxation phenomena have been identified by various research groups. In 1977, John Kerr said, there is a universal dielectric response at gigahertz to terahertz range. So this is by measuring dielectric properties, okay? So as you know, optical properties like refractive index and loss and the dielectric constant are all interrelated. So if you measure one, you can convert them to the other, okay? They found this trend in all disordered materials. So this is all disordered material. All glasses have these features. So this is perhaps maybe what Dr. Wilkinson was telling you. There are many, many relaxation phenomena going on. And if you want to look at, you have to go to other frequencies to look at all the phenomena, really, okay? So wouldn't it be nice to have a spectrometer where I can put a piece of glass? It gives this whole spectrum. And yeah, of course we don't have one like that. You know? But the groups who have been studying this, they've been using two tricks. One is they will gobble up electronic bridges and network analyzers and the terahertz spectrometers and measure real and imaginary part of dielectric constant and then plot them all together. And another trick they were doing is they will pick very low temperature, simple molecular glasses. That is the trick, because it is easy to measure them. You know exactly the molecular structure. So for example, they published a lot of results on glycerol. Glycerol is a glass with a very low glass transition temperature, 190 K, you can see. it melts at 293 K. So obviously, if you want to observe more phenomena, you may have to remove a lot of thermal noises. You have to go to low temperature, so you'll be able to see more resonances coming out of your material. Anyway, so we don't have a spectrometer for that, so obviously I won't be able to do all of them for the glass. But I've been in talks with Professor Tidrow, who is in Alfred. He's a low gigahertz electronic materials expert. So we've been talking about it, but it's going to cost probably $2 to $5 million to assemble all the dielectric equipments, which will cover such a wide range of frequency. The equipment, once it's ready, you can put glasses and study them. Anyway, so that brings me to the terahertz time domain spectrometer, which we have been using. So in this case, how the waves are generated. The waves are generated using a laser-gated photoconductor. We call it antenna technology. What you see here is it's basically a gallium arsenide substrate with a surface textured and with a gap in between. And the gap is the one which is going to excite the charge carriers here. So you hit it with about 90 femtosecond near IR pulse. And when you hit that, and remember, you have been grounding this, both sides of this substrate so that you can pull charges out of this. So out comes about less than 500 femtosecond terahertz pulse. You can call it as a continuous wave, okay? So to detect terahertz waves, you use the same technology in the reverse. So this is a typical setup you have. You start with femtosecond pulses. You divide the pulse into two parts. One send it to detector, one send it through a delay, time delay, and that's why it's a time domain spectrometry, and pass it through a terahertz emitter. This is the antenna here. And then you can use parabolic mirror to pass it through your sample and detect what comes out, really, okay? It's just like any other spectrometer. You can open and put the sample in. So there has been a few groups who have been trying to measure boson peak directly, and we are still having problem. I just wanted to give you one example. This is a paper just published in 2024. They've been trying to measure boson peak in a Baltic amber glass, and initially they couldn't see any boson peak, and then they cooled the glass to about 15 K, and then they see a boson peak, okay? So you can clearly see the challenges involved, and I am talking to the spectrometer company. Eventually, we may have liquid helium cooling. We may be able to see something, but right now, we're not doing that, okay? All right, so moving along, the early results of terahertz properties of glasses are.
Excuse me, since you're talking a lot about the boson peak, could you please explain the students what kind of information, what you get after you detect or you measure a boson peak?
Yeah, once you measure the boson peak, thanks for the question. What you're really getting is, you're getting a good idea of density of states, which are, normally you will see tails in glass on both the ends of the band diagram. So that will give you the insight about the extra density of states when you form in your glass, when you quench your glass, really, okay? That's a big difference between a crystal and a glass. The crystals won't have this extra tail of states around the band diagram. So that's the information you get. From that, you can clearly see it controls all the dielectric properties, optical properties, and electrical properties, all controlled by the states and the band. So the earliest report of data I saw in literature came from Dr. Mira Naftali. She's from National Physical Lab. Here is a plot of absorption coefficient and refractive index, and this is a frequency. You can see from 0 to about 3.5 terahertz you are seeing here. And the data shows absorption and refractive index for quartz crystal and fused silica, okay? So you can see the refractive index, or this reasonably flat lines. These are refractive index for crystal versus glass. For glass, of course, the refractive index reduces because of the disorder. But the absorption has this kind of feature. It doesn't have any special peaks. You don't have peaks, absorption peaks. So we call it as absorption spectra with no feature, but typically increasing monotonically this way. I know for glass science, it may not be that exciting, but for optics and photonics people, they love when the refractive index doesn't change much with frequency. There'll be no dispersion. They can design their components without worrying about loss. So it's a good thing, really, okay? So there was a Storm-Schulman power law report in the literature, and that was correlating the absorption coefficient times the refractive index can be described by a K material-dependent parameter and an exponent beta. And the data set for glass, the beta should be just 2, okay? Some of the things we were trying to do is really check that, and this is the Storm-Schulman power law, and you can see K can be calculated for any material in any glass composition, and K increases the 4th power of refractive index because this K is n squared plus 2 over 3. It also increases with the density and amplitude of charge fluctuation. So typically, in multi-component glass, you can expect larger refractive index of terahertz phase, okay? So Naftali group also reported refractive index for common optical glasses. You can see BK7, Pyrex, dense flint. They reported commercially available glass composition. There was no report on what is the structure and what is the effect on the terahertz properties we are measuring. So, so what happened is, this is our motivation. We don't have a comprehensive terahertz property model of glass right now. We know all these things are happening, and we have talked to optics and sensing, all this community. Honestly, I've talked to a lot of physicists and electronic scientists and terahertz scientists. Whenever I talk to them, don't tell me about the glass structure. Tell me what is the refractive index, what is the loss, because I want to use it for something, for my experiment, or I want to send something. So the property measurement is the most important thing they wanted. So the applications need terahertz property data. So what we decided to do is, we are sitting in an Alfred, we're going to measure terahertz spectroscopy using terahertz spectrometer we have, and we're going to at least quickly generate. I know it sounds like empirical cook and look, but remember, you need at least some data when you have nothing. So we systematically varied glass composition and measured refractive index, and we used all well-established spectroscopic techniques to characterize the glass structure. So that way, we know what glass structure we are talking about. We measure correspondingly refractive index. We know exactly what the refractive index is, really, okay? And then we can go back and forth interpreting. We have also used femtosecond laser radiation to change the glass structure, and we have measured refractive index changes in the terahertz field as well. I'm not going to talk about that because just for the time limitation, I'm just only going to focus on glass composition and terahertz properties. So this is a typical spectrometer we have. You know, everything I mentioned about the emission, you know, laser beam hitting a target, all this are nicely packaged right here. And you just open this lid. There is a slit. You can put your sample in, and you can use the program to run and get spectrometer data. So the positive things are, you can quickly collect spectra. It takes only a few minutes. It doesn't have any cooling. You don't need liquid nitrogen or helium for normal measurement. And also, you can heat or cool sample if you want. And we have a sample holder, but we cannot heat to too high temperatures, okay, at this point. So typically, you put the sample in, you first get the terahertz signal, and on Fourier transform, it's converted into electric field, and you convert that directly to the absorption coefficient and refractive index. So the beauty about this technique is once you collect the spectra, you can calculate refractive index and absorption coefficient, and directly from the field data. This is what, this is the raw data you get. You have to calibrate with the nitrogen or high purity nitrogen, and finally you get the absorption coefficient and refractive index data right out of the same sample, same data set. The software also gives you real and imaginary part of epsilon prime and double prime. This is permittivity, because permittivity and optical constants are related. You can convert from one from other. So basically you can measure refractive index, absorption coefficient, and also real and imaginary part of dielectric constant. Since we started in the past about 3-4 years, we have published about 8 papers. And you can see it's all published by, the first author is Nicholas Dostoevsky. That was his PhD thesis. He is now working for Corning. You have guessed right. He did finish his PhD about 2023. What we have done is we have measured structured terahertz properties of borosilicate glass, telluride glass, and a set of chalcogenide glasses, because we wanted to not only generate data set, we also wanted to generate, we know that terahertz refractive index, as everything else, depends on polarizability. We wanted to add polarizing ion in the glass. We wanted to look at more covalently bonded glass like chalcogenide. So we wanted to quickly collect oxide glasses, non-oxide, and telluride to see what is the range of property we are getting. And I'm only going to talk about just 2 of those papers, and I'm also only going to talk about briefly the results. Everything I'm showing here, they are electronically available with me. You can find and read, or if you want, I can send you all these papers. The latest one is the featured special issue paper in Journal of American Ceramic Society, just last year. This is the one result I'm presenting here. Remember, our approach is use well-known spectroscopic techniques to characterize structure, and use terahertz measurement, and then correlate these two, okay? That's the only way we can do for now, until the comprehensive model comes out. And so you can see we have collaborators here. Obviously, we didn't do it alone. You can see Professor Monk is a co-author here. You also see Randy Youngman as a co-author here. So instead of going through all the details of the result, I'm only going to show you what is the composition and what we finally got, okay? So this is a ternary we focused on, and you can see we prepared 2 series of limited glasses. I don't believe in making tens of glasses. We wanted to make select glasses to see. We were interested in, we know a radium-emergent ring and Dan-Braid ring are present in the borosilicate glass, so we selected composition in such a way we know the R and K are varying in this. So we prepared these glasses in our lab and characterized in using our spectrometer. And these are the other techniques we used. We used the boron magic angle spinning NMR. We used infrared, and we used Raman to collect spectra and also decompose the spectra, assign various bands to the structure, and then we tried to correlate that to terahertz spectrometer data. I'm jumping to the very final result. This is just to show you one example. This is for a sodium NAB silicon series. You can see that's the composition, and you can see as you vary sodium from 10 to over 40%, your refractive index is, sorry about that. Go back. Your refractive index is widely changing from almost 2.8 from 2 here. And what we did is, you can see, except for certain low alkali composition, these are pretty straight dispersion-free property here. So we took about midpoint, 0.5 terahertz. This is a 0.5 terahertz refractive index, and we are plotting against R values and K values. This is to show you how strong a function of glass composition is our terahertz properties. And from all of our structural data, we also know what seems to be happening is when we are at 40 mole percent of soda, we are really talking about only bridging oxygen, and the silicate and alkali subnetworks, they all are existing, and all sodium is used up as a charge compensator for the BO4 tetrahedra, and some of the BO3 is converted to BO4, and we are getting lower terahertz. And in the case of 10 mole percent sodium, we have more depolymerized network, and that's the reason we are getting higher refractive index. So at least we are trying to use polymerized structure versus depolymerized structure and tying that to refractive index in terahertz frequencies. Okay, so this is after 6 papers, this is what we published. Meanwhile, we already collected data on telluride glasses and a series of chalcogenide glasses, anywhere from unary, binary, and ternary chalcogenide glasses. So we plotted them all together. I'm going to show you some of this data. So you can see tellurides, obviously higher. You have tellurium heavy ion, polarizing, high polarizability, you will expect. So higher refractive index. And you can see borosilicates are here, chalcogenides are somewhere in between here. And I also want to point out to you, you see for tellurides and borosilicate, the data ends somewhere here, around 1 terahertz. For chalcogenide, we get data over 2 terahertz. So I want to point out to you, one of the problems is how powerful your terahertz source dictates how much more data you could collect, because if you don't watch for, you hit the noise floor in the spectrometer, so you have to cut off where the data is to get a real data set for you, okay? That's why. So you can see the chemistry of glasses make a big difference, not only in the range we can measure them, and also the actual values of refractive index and absorption coefficient. And you can see the absorption coefficient curves, they all look the classic increasing feature which we have seen in the law. I told you what? So after doing this, what is the final purpose of doing this? We wanted to find 2 things we wanted to do. One is we wanted to give enough data to optics and photonics people so they can look at, they can select what absorption they can tolerate, how high a refractive index they want, what family of glass they should be using, really, okay? So you can clearly see red telluride, if you want high refractive index, you may have higher absorption too. You will select telluride glasses. If you are low refractive index, low absorption, borosilicate, and chalcogenide in between. So this is one of the data set we wanted to produce, okay? The other thing we wanted to produce is, remember I talked about K and beta at the beginning? The equation, the power law says, the K values, if you calculate, and if you plot, and if you get the beta, the exponent value beta, for all glasses, it should be 2, okay? So we wanted to see whether we are getting 2 for all glasses. It turned out to be, no, we are not. So if you look at the plot, you can see these are borosilicate compositions. You're getting beta values close to 2. There is a huge variation because we varied the composition. And the same way, the chalcogenide have a huge spread of beta values, and telluride have, again, another set of values, not exactly 2, somewhere between 1.4 and 2. So the power law, which is an empirical law, of course, is really not sufficient to capture all the variations happening in these glasses. So with that, one of the things we are trying to do is we of course would like to work with anyone to come up with actual model to predict all these things. And I'm hoping, Dr. Wilkinson, when you see the peak, boson peak, I'm sure Dr. Wilkinson is seeing a very complicated energy landscape. So we can start with energy landscape and actually predict all the relaxation I've shown you for glasses, if you can, and possibly predict terahertz properties. Then I don't have to measure anymore, okay? But that's not happening anytime soon. And meanwhile, the applications I'm talking about, they are tens of billions of dollars worth of business. People are using terahertz waves in all the security, all the medical application. So we will continue measuring glass property. Our goal is to add more data. And also we want to share our data with everyone. That's our goal. As we have now, as of now, we sort of have all empirical relationships, and some of them are scaled a bit. That's the kind of relationship we have. So we don't have a comprehensive model, okay? But we have useful properties we have actually measured, and we know that glass composition and glass structure affect this property, okay? So right now, these data set and these relationship we are talking about, this correlation, are very useful for optics and designers and physics experimentalists if they want a piece of glass which will reflect or transmit or do something with the terahertz beam for the measurement, whatever measurement they're doing, or whatever application, we may be able to tell them which glass they should use. Another advantage about, we mainly first focused on silicate glasses, because as you know, silicate glasses are the ones you can cheaply make them, and you can make them in any shape. You can make sheets, rods, any big shape if you want. So for application, this will be very useful. So with that, I'm also trying to wrap up. I don't want to put too much. If you want to know more, I just want to quickly point out to you some literature. In 2024, this is the collection of all the data that Nicholas produced out of his PhD, published in the special issue of Journal of American Ceramic Society. I can send you the paper if you're interested. All the data are listed. We are ready to give the data to anyone who want to use it. By the way, we ran some of the spectra also through NIST. NIST has their own built-in terahertz spectrometer. We sent our samples, some of them to them, and we compared their spectra to our spectra. The deviation is within 0.1 to 0.2%. So we were getting the same kind of data NIST is getting using their spectrometer. So you can read that paper. In 2023, there is in Nature, there is a terahertz time-domain spectroscopy primer. It literally tells you everything about the technique, what you should look for. So that's a very good paper to read. And this is Mira Naftali's early paper, Fundamentals of Measurement in Terahertz Time-Domain Spectroscopy. She's an electrical engineering scientist, a part physicist. She knows a lot about metrology. So this book is edited by her. So if you want to make terahertz measurements on anything, biological cell or glass or cell, you should read that book, okay? That's my recommendation. Remember I told you I do work on ultrafast glasses. I'm only putting one slide here. We've been doing a lot of work on using femtosecond pulses, not to write structure in glass, but locally modify the glass structure. And we have shown we can do, and we have also used some molecular dynamic modeling to study the laser interaction with the glasses. And in one of the papers, we have used laser-modified glass structure and predicted the moieties and species, Q4s and Q3s, and we also measured terahertz properties of those glasses, okay? So in case you are interested, so I would, I'm going to stop here. I have to acknowledge, of course, all this work is not possible with a dozen or so graduate students at Alfred. They work very hard, and everything you see here is because of the grad students. So, and my college completely supports me. The Inamari professorship does help me to do what I want to do. With that, I stop here, and thank you for your time. And I welcome any questions you may have.
Thank you. Thank you very much. I'm really surprised to see how high the refractive indexes go in this terahertz range. So why is that? Why the increase so much from the visible up to the terahertz?
Couple of arguments. One is the glass chemistry. We change the glass chemistry. You are changing ionic as well as electronic polar stability. And the polar stability change is the one main thing causing. I'm sorry. Yeah, the question was, the question was, why do I see such a big change in refractive index? Okay, so my answer is something along the line. The refractive index is closely tied to polarizability, and the more you balance between ionic polarization and electronic polarization in your glass composition, more control you will have on the terahertz properties. So obviously, if you have more electronic polarizability, polarizing ion in your glass, your refractive index in terahertz will be higher. Okay, so that much we know so far. And that means when you say higher, you know this, the optics community always want higher and higher refractive index. Because for a lot of high energy physics, they really need to focus beams on certain direction, they have to direct beams, so they always need material which will have high refractive index, in a certain wavelengths. That's what they're in for. For example, the satellite work I talked about. The satellite work I talked about, the interstellar species you're looking for, you probably need very high energy to beam to collect spectra. So that also dictates how big a system you have. So the absorption, the one disappointing thing you might have noticed, because in glass community, we love absorption spectra. We love curve fitting. We love decomposing. I'm not using deconvolution, Dr. Bolton. So they are all useful, and they're all also very good. And remember, we also want to use well-established techniques so that we know what structure we are measuring. Because from terahertz, you don't get directly any structure signature, okay? Unless you have organic molecules. But if you look at molecular glasses and large organic molecules, there is a lot of terahertz spectroscopy you will see in those literature, in biology and chemistry. Yeah, sorry, go ahead. Sorry.
Thanks for the lecture. So my question was, I was just curious to know if terahertz measurements might find applications in things like phase transformation, such as probably salt formation when you're looking at in situ detection, like in a waste treatment plant for like salt formation with the waste treatment up in Hanford. Just curious to know if the terahertz frequencies or millimeter wave detections will find any use in such applications.
Yep, you will be surprised. There are already terahertz scanners being used for scanning certain thing. You probably heard about drugs in the mail. There was a time drugs were being trafficked by mail. So it turns out some of the drugs have chemical signature in terahertz waves. So they had a technology developed which basically uses terahertz wave passes. You scan your envelope through the terahertz wave. It's like an airport scanner, and then you get the signature. If it's a drug, you will see that. Really, it's very similar to the airport scanner you're seeing. The airport scanner works in about 50 gigahertz. Okay, it's non-ionizing, so I won't get radiation through, but it only will tell me the contrast in dielectric properties between a knife and a piece of clothing. Okay, that's the contrast simply. But terahertz waves can give chemical signature. By the way, explosives have terahertz signature. So if there is an explosive inside a box, so you may want to run handheld terahertz spectrometer. You'll be able to collect that. Some of these technologies do exist. They may not be the perfect one, but they do exist now, really. I'm more interested in knowing what glass they would like to use for any application. So, but the application of terahertz itself, it's a big field, and there are companies making all these products, really. So if you go to some of the SPIE meeting, you will see that.
So there's optimism that we'll find applications for it in like a waste treatment plant to detect like salt formation on the layers.
Yeah,
Okay.
yeah. So I would love to do a full-blown integrated photonic project for terahertz application. Where is the funding? There's always a problem. When I was in PNL, one of the projects we did is, I think Professor McCloy was also part of the team. We used chalcogenide glasses to look for long wavelength chemical signature in remote sensing. The way it works is you make your glasses layers and perfect structures, and then the signature will pass through your glass structure. That's how you detect. So the same way, anything which has got terahertz signature, you can let it pass through a window. That window will be a glass. That's what I'm interested in. I'm interested in producing glass which can transmit, reflect, deflect terahertz waves. And then the community will be able to use it for any application. Right?
Thank you.
There are also terahertz cameras, by the way. So there are lenses in the front, just like your iPhone has now several glasses, right? iPhone has several pieces of glass in the front. So the same way, if you have a terahertz camera, there are terahertz cameras being used in military, and if it becomes civilian use, we will have them maybe. But the front, because you cannot have every electronics exposed, you're going to have a piece of glass. But the piece of glass should have terahertz transmission, in and out. So I'm more interested in finding glasses for those applications than just simply doing. But at the same time, I'm always trying to tell them, you really need to know glass science, glass structure. And they're always ignoring me, as usual. I can tell you another story. I had a project where we were developing glasses for neutrino physics measurement. And we had a fantastic project. A PhD student finished thesis in Alfred. We came up with a new composition which will work way better than the standard PMT glasses they were using. And I called the group which won Nobel Prize for neutrino, and they were planning next experiment, and they were very nice. They said, oh, we really appreciate you contacting, but we are happy with the glass we are already using. Okay, so you were kind of telling, do you know the glass structure changes? We can change the composition. So I'm always struggling, but that doesn't bother me, because if they are my client, it's my job to produce the glass they want, than lecturing them about glass structure. Okay, so I can't do that because they want me to. Hey, stop talking about the structure, but can you give me a glass for my terahertz application, which has got 5 refractive index? Okay, so that's what we are trying to do. Can we quickly, and of course you can see we cannot measure all the glasses experimentally, so that's where I'm hoping. And if Professor Wilkinson is not busy, I'm joking here, and of course, if some of these problems it takes enormous research power to solve it, really. As you can see, the disordered material, like glass, has all those relaxation phenomena spanning over 18 orders of magnitude frequency. Okay? This is already observed in some molecular glasses. Okay, so I'm sure if we have all the equipment and if we do all the modeling, we will be able to find the same features in all of our glasses. Maybe there will be variations because of the chemistry, and we'll be able to do the whole thing. Like, we never have to measure again, But that's something I cannot do because I don't have. You probably can see me. I don't have a modeling experience. I'm an experimentalist, but I would like to work with modeling researchers. I've done that a little bit, so that I'll do that.
Thank you. Well, I guess, is there any other very critical question you want to ask?
By the way, we can easily measure, some of the things we can do for you, we can easily measure samples for you, and we can share the data with you, and we completely want to be transparent with all the data we are measuring.
Thank you.
This is actually funded by public project, so you have right to look at all the data we have, and we continue to add more data. Currently, a PhD student, Kate Mathis, is working on other glass system data. She's working on soda lime, and she's also working on quaternary chalcogenide glasses. So in a couple of years, there'll be more data added to that. So we'll continue to do that, okay? So you will see that. So those will be available if you're interested. And we are always open for collaboration. And you can see some of the experimental part, my group is very strong. But I completely open to modeling and model development. Some of this data can be used for developing the comprehensive model we are talking about. Because earlier it was zero data. Like, I remember when I only saw for silica, boson peak for silica, or boson peak for pure B2O3, but there's nothing else really. So now we have at least more data, and we know in some empirical way the glass structure does affect the terahertz properties.
You definitely have to send that data to the Jena group to enlarge their database. So with that, I think I'll thank you again very much.
You're welcome.
Let's
Thank
give
you.
him a round of applause for this talk. And now I'm really thankful to Professor Ben because this lecture on ion exchange was supposed to be given by an old professor, Bill LaCourse, very good old friend of mine. Unfortunately, he had some health problems, and so Ben kindly agreed to give Professor LaCourse's talk, despite the fact that that's not very much his own cup of tea, right?
Absolutely.
But I'm sure he'll do a great job. So thank you, Ben. Thank you very much.
Set it up. You can get your set. Yeah, so you've seen me already this week, so I will skip my own introduction. But I've came to this presentation through Bill LaCourse, Dr. William LaCourse, and the reason I got interested is because there's some very weird structural phenomenon, and as I mentioned in my introduction, I'm pretty much interested in all aspects of structure wherever they may arise. So Bill's doctoral student, Jacob Kasperik, is going to give the bulk of this presentation, and you'll see me at the end, and I'll come back with some an evaluation of some recent studies that show some interesting structural changes that accompany ion exchange and may deviate from the more typical model that Jacob's going to talk about.
Okay, can everyone hear me? Everyone can hear me? Cool. So if it's not clear, I am Jacob Kasperik. I'm up here in this red sweatshirt. Obviously, I'm not Ben, nor am I Dr. William LaCourse, but I really do enjoy working with William LaCourse a lot, so much so that, of course, we're different people. Doc is usually a lot shorter than me. I am indeed, in fact, taller than he is. Another fun fact, he is born before 1950, and I am born after 1980. There's a little bit of age difference, but let me tell you, he knows a lot more about ion exchange than I do. I still know some, but my favorite part is what we have in common. Now, what do we have in common? Well, we get to the lab way too early. I have been in the lab at maybe 6 a.m. and Doc walks in at 7 and he goes, "Why are you here?" And I say, "I don't know, I follow what you do." Similar things. Another fun one is weekends. I see him every weekend in the lab working. And he goes, "You're the only grad student here?" And I go, "I don't know, I just thought I was supposed to be here." So I also work on the weekends, and of course, the love of glass and ion exchange itself, and all the crazy ideas that we share with each other. In addition to the fact that whenever you're looking for Doc, it's really hard to find him in the labs. He likes to disappear. And I've been known to do that as well. And then sometimes we leave a mess around the labs, but I usually follow him around and clean up after him, but I also tend to leave stuff in the lab. So, but that's just a little fun fact about Doc and I. On to the main topic. So here we have 4 pictures. We got some yacht windows. I get to experience the laser pointer now. Yacht windows, aircraft cockpit windows, display phones, and EpiPens. Now the question is, what do all these things have in common? Well, of course, if it wasn't obvious, ion exchange. They're all ion exchange products. Now, what is ion exchange, and then what can it do. So the objective of this talk is to go through all the basics and what you would see if you wanted to research ion exchange, and then how to do some analysis and understand what the process is about. And then later, Dr. Moulton will go into more specific studies about structural things. Now, you could consider that the ion exchange is the exchange of one mobile ion for another. I think you could expand it probably to the exchange of mobile ion for just another mobile species. What can it do? That's really important. Well, there's kind of three main broad categories that you could use ion exchange for. I get to experience the mic. Color, waveguide, and then strengthening. We'll swap out. Okay, problem solved. We're great scientists. Strengthening. So I'm going to quickly go over what color is, and then what you can also use it to make waveguides, as well as the strengthening, which is the main thing. There we go. So usually when you think of ion exchange, you think of the strengthening. Historically, it's actually been used for coloring glasses. So some old stained glasses were also colored via the ion exchange process, usually with a silver nitrate or a silver sulfate paste. And then you can get a yellow color in addition to some other colors based on the size of the silver nanoparticles that you grow. And then personally, my favorite is a copper exchange. So what you can do is you can take a soda lime silicate glass that either has some tin in it or is float glass, and you can do a copper exchange. So you can put copper 2+ or copper plus into the surface of the glass, and then you can reduce that copper down to elemental, and then you can get a nice red color on the surface of the glass. So that's one example of where you can use ion exchange. Another example is you can make waveguides, or you can make gradient refractive index lenses, and this is done by swapping out the ions on the surface of the glass, so you can change the refractive index, and then you can make better fiber optics or gradient refractive index lenses. The main thing here, obviously going to talk about strengthening. So when you think about strengthening glass, there's usually two main categories. You can either thermally temper the glass, or you can also chemically temper the glass. The main thing here is that both of those, actually I'm going to go back one, both of those, one of the main difference is the geometry type. So for thermal tempering, you can usually only do flat samples the majority of the time, and then you're dependent upon the thickness of that sample. So usually tempered glass can only go down to 2 millimeters. If you want to strengthen glass below 2 millimeters, you'll probably want to do an ion exchange on it. What's really common in the field, or what you'll see when you're researching, is you'll see something that looks like this. So this is a stress profile for a thermally tempered glass. On the top axis here, you have the tensile strength and the compression strength, and then this is the glass thickness as the y-axis. So what's actually happening here is this curve is the stress profile in the glass. As you cool down that tempered glass, you cool down the outside faster than inside. So the structure doesn't have time to fully relax, and then you form a compression, and that compression is followed by that thermal gradient in the glass. In comparison, for chemical strengthening, we have a more stepwise fashion. So again, the top axis here is tensile strength, and then compressive stress. In this case, since that exchange is much quicker and is not as gradient as the tempering, you have a more stepwise fashion where that the difference between the surface and the bulk, the surface and the bulk is much steeper gradient.
Jacob, and just a comment, and the level of stress is much higher, right?
Yes.
For
Yes.
ion exchange.
Yes. Yep. So you'll acquire a much higher strengthening from an ion exchange than you would out of a tempered glass piece. Now, so let's say you want to do ion exchange yourself. Well, there's some things to consider. First thing, we're gonna look a little crazy. Parameters, equations, and analysis. Now, the main things with parameters is you want to know about the glass composition you're going to use, the source of ions, the temperature, and the duration, as well as the type of method you're going to use for your ion exchange. Some important equations include the diffusion coefficient, activation energy, the stress, the network dilation. So you'll actually see these equations pop up on the slides when they're relevant to what I am talking about. And then in addition, I'll talk about some analysis. The two main ones, sorry, I'll go back. Analysis, so talk about how to find concentration profiles or stress profiles, how those look. And then, of course, there's also your general properties that you can always find about the glass system, as well as structural and coordination information. So to start is, what type of glass can I use? So compositions. The main question you want to ask yourself before you do an ion exchange, you have to ask yourself if your composition of glass even has a mobile ion to begin with. If you have a mobile ion, you can probably do the exchange. Now, very common compositions include silicates, so borosilicates, aluminosilicates, aluminoborosiliciates, phosphates, chalcogenides is hidden in this border. And then in addition to those compositions, usually, or not usually, but some of those compositions will have different effects. So very common effects include the mixed alkali effect, the modified random network, the alumina/alkali ratio, and then you can't see it because it's hidden, but the boron coordination. So these effects that are present in certain compositions will influence how effective the exchange is. So something to keep in mind. But I'll further talk about silicates and then the mixed alkali effect, as that's what's most commonly done is silicates. And then I'm most commonly, and Doc is a huge fan of the mixed alkali effect, so talk about those. Did we freeze? We might have been frozen. I have too much information. He closed it and reopened it. Let's get back to it. It's fine. Okay, silicates. Silicate systems are the most exchanged, so all those examples that you saw in the pictures, the display window, or the yacht window, the cockpit window, your display phones, EpiPens, those are all some type of silicate. Well-known commercially available glasses, I'm sure we all know Corning Gorilla Glass, Dragon Trail, Sensation, all these very highly well-researched, well-developed ion exchange glasses. They're all some type of silicate. And then, of course, you have normal float glass, so normal soda-lime silicate glass for bottles and containers. That's not usually ion exchanged. It's just not profitable. It's not as efficient as other compositions, as well as the profit margins aren't there to go and introduce and develop and implement the ion exchange process into those manufacturing processes. So, and it's also way more time consuming. So in exchanging normal soda-lime silicate glass will usually take up to 16 to 24 hours of time in a bath to get a micron depth or a case depth of 40 to 50 microns. So that takes a lot of time. And to do or implement those processes in the container glass or bottle glass industry, you're going to also create a lot of additional chemical waste. And like I said before, it's time consuming. The main effect in silicates is usually the mixed alkali effect. So In the case 1, where you have an ion exchange, or you ion exchange a single alkali glass below the annealing point, and then in this case, what will happen is those sodium sites on the surface are occupied by potassium for less depth but higher overall strength. And then in case 2, you can ion exchange a mixed alkali glass that was formed from melting below the annealing point. And in that case, since there's already present potassium sites in the glass, you can actually get a slightly quicker exchange, but an overall less strength due to the fact that you have less compression. And now I have a graph here to display exactly that. So on this graph on the y-axis, I have surface stress. On the x-axis, I have the depth in microns. And then this orange dotted line is the, I believe it is, yes, it's the single alkali glass. So you see you have, at the surface, you have a much higher strength. As you go down, it dips. And then for the mixed alkali glass, the yellow dots here, the stress profile is not as strong up front for the first 20 microns. It actually leans in more into the bulk as a little more effective for overall strength, as it's not as time-consuming to do. The next thing is you have to acquire your ions from somewhere. So if you're going to do an ion exchange, you're going to need ions. So your source can either be a salt bath, a salt paste, aqueous spray, vapor deposition, or glass interdiffusion. Now, all of those have the issue of contamination. So if you're on an industry scale or if you're doing this in the lab, you can run into the problem where even if you have less than, we forgot to change that. If you have more than 100 microns or 100 ppms of calcium, it'll actually impair your strengthening. That's due to the fact that calcium acts as a blocking ion and inhibits the sodium or your potassium from further diffusing into the glass. You can also run into the issue where you exhaust your salt bath. So say you have a potassium nitrate bath, you put your sample in, enough sodium comes out of your glass, and then now you don't have the correct concentration profile or concentration gradient in that salt bath, and you can now no longer exchange that glass. Very simple equation of showing what ions swap. So the two ions with the two letters here with the line over them are the ions that swap out and in the glass. The salt bath. So this is the most common form of ion exchange where you can get your ions from. Usually they're salts of either nitrates or sulfates. Usually the industry standard is a potassium nitrate or a lithium or sodium nitrate. You can see here the temperature ranges of those salt baths, or all those nitrates and sulfates. You have a large range of temperature, so depending on that glass composition that you're trying to do, you can adjust what salt bath you're going to use depending on that composition. And then you can also have more leeway to create a certain temperature or a certain bath that has a certain temperature range through eutectics. There's also the idea that you can use a multi-component salt bath. So you can combine potassium nitrate and sodium nitrate to increase that exchange as well. And then one of my favorite parts about ion exchange is it's not it's kind of accessible. So even if you have a stainless steel beaker and a muffle furnace, you can do an ion exchange in your lab. It doesn't take much, but you can also get really impressive equipment. So you can get a specialized furnace to do your ion exchange where you have a dedicated furnace that has a stainless container, and then you have that bath, and then usually a mechanism to take your samples in and out of the bath. Otherwise, I do it manually, and it's very painful. So from there's also paste, aqueous spray, and spray deposition. So the idea here is that instead of submerging your glass into a bath, you can apply a paste either manually by hand, usually by mixing potassium nitrate and kaolin or alumina into a slurry, and then you can apply that onto your piece, onto your glass, and put that into a furnace. You can also use a spray gun and make an aqueous solution and then apply that via the spray gun, and then do a heat treatment, and then that will also do the ion exchange. And then the other thing is a vapor deposition. So instead of just applying through a spray or a paste, you can actually cause the exchange to occur via a vapor deposition, where you take that solution. So in this example, it's just the potassium chloride and H2O. And then you can pressurize that, turn that into a vapor. You can then control that vapor to make sure you have the right droplet size, enter that into a chamber where your piece is, and then you can proceed to do your ion exchange on that glass piece. Now, the last one here is some of my own work, but so here I have a mixed alkali silicate glass, and we're going to talk about glass interdiffusion. So my source of ion is both external and internal to the glass. So in this case, I did a sodium exchange for 24 hours. On this graph is just, this is a SEM EDS mapping that's been averaged. So that y-axis is just normalized atomic percent, and then the x-axis is just the distance into my glass. So I do a sodium exchange, so sodium goes in, and then the potassium comes out, it levels off. After that, yes, so this little yellow box is another equation. So when you're doing your concentration profiles, there's a couple different ways to acquire the diffusion coefficient. This is one very common one where you have this error function where you can then fit this curve. You can then fit this curve with this equation, and you can pop out the diffusion coefficient. There's also a couple of them that allow you to approximate it accordingly as well. So after that exchange, I then do a lithium exchange. Again, y-axis is just my normalized atomic percent. X-axis is just the distance into the glass. And in this case, I now put lithium into the glass. So you can see that then the sodium comes out. And during the exchange, that sodium also goes inwards towards the glass. Finally, after that, I do a heat treatment on these glasses. And you can see that, again, y-axis is just normalized atomic percent. X-axis is just the distance into the glass. The pink line here is the potassium. The purple line is the sodium. This is the same glass you saw as before. I just did a heat treatment on it at 3 different temperatures. And you see that at a higher temperature, that sodium actually diffuses both towards the surface and then towards or into the bulk additionally. So you can also do an ion exchange from the glass, from within the glass. Finally, probably the most important part, well, I guess they're all important, but another very important part that you can tie together is the temperature and the duration. So both these things actually kind of work against each other. So at a lower temperature, you'll get less depth, and you'll get less relaxation. At a higher temperature, you'll get shorter time, but more relaxation. So like Dr. Wilkinson was talking about earlier, this is going to be stress relaxation. In addition, you'll have a short time. If you do a short time, you'll get less depth. And if you do a long time, you'll have more depth, but you'll also get more relaxation. This is a very generalized graph of the y-axis here is just the modulus of rupture. The x-axis is an ion exchange duration, and then you can, the other y-axis here is case depth. So the depth is proportional to the square root of time. So as you do an ion exchange longer, so these 3 lines represent different temperatures. So as you do different temperatures, you'll actually have, obviously the modulus of rupture will slope off or turn downwards or decrease, and that's due to the relaxation that's occurring in the glass. So you may wonder, well, how do we want to avoid that relaxation, so how do we do that? Well, there's a couple different workarounds. So there's 2-step exchange where you do an exchange above the TG, and then there's also an exchange, oh my goodness, I'm talking really slow. 2-step exchange and then a exchange below as well. And then there's non-isothermal treatments as well as, oh man, what does that say? Yes, developing compositions that minimize relaxation. So those commercially, those really nice ion exchange glasses, those have been developed especially to minimize relaxation. Again, there's just a simple equation to this equation. Arrhenius equation is usually to find that activation energy. And then this is a case of non-isothermal treatments. So the solid line without dots, again, so in this case, the y-axis is your compressive stress, x-axis is the distance from the glass surface. The solid line here is a conventional one-step case. The line with all the markings is a non-isothermal hold. So what you do here in this case is you take that ion exchange and you do a high temperature exchange, and then you actually transfer or you alter the bath temperature downwards, and you can see how the profile for this one shifts. I lied, they're swapped. So the solid mark ones is the solid, or is the single step exchange, and then the solid line one is the non-isothermal hold. All right, on a method. So there's standard, so one step exchange above or below the TG. You can also add more steps. And then there's specialties, which I'll get into later. But so the classic cartoon that you always see with ion exchange is something that looks like this, where you have your single ion going inwards into the glass, and then your smaller ion coming out. Very fun cartoon that you see all the time. Standard one-step ion exchange. The sample enters the salt bath below the TG or annealing point, and that strength that you're getting is actually coming from that compression of the network, and that's forming the compression network, and it's not fully allowed to relax. In the second case of a one-step exchange, you can actually do the exchange above the annealing point, above the TG, and this strength is actually coming from the formation of a lower coefficient of expansion glass layer. The big distinction between these two things, besides the fact that it's above or below, is that if you're doing the exchange below the TG, you need to swap in an ion that is bigger than the one in your glass. In the case of number 2 here, if you're doing a sample exchange above TG, you have to use an ion that is smaller than the one in your glass. And this is Fick's second law that governs how all the diffusion works. Two-step exchange, similar to the one-step exchange. Usually you'll do a glass below or above the TG and then below the TG, and then this can speed it up, usually due to the fact that the exchange above the TG is quicker, and then the exchange below the TG is not as, you do not have to do it for as long a duration. And again, the strength in this case comes from the fact that the network is not allowed to fully relax. Recap of the critical points. So remember, if you want to do an ion exchange yourself, you're going to want to know what your composition is. You're going to want to know where your ions are coming from, what method you're going to use, and then you're going to want to decide the temperature and duration of that exchange process based on that composition of your glass. Techniques and analysis. So you have your ion exchange glass made. You want to do analysis on it. The main ones in this case, oops, too far. The main ones in this case are concentration profiles and stress profiles. Those are the two unique analysis or concepts within the ion exchange. In the first case, you can use to find that concentration profile or to find the depth profile of the exchange. The main one that the majority of people use is SEM EDS. So this is SEM EDS. This is an example. So this green EDS mapping is sodium, and this purple mapping is actually potassium. So either you do an EDS mapping or you can do a line scan, and then that's usually done on a SEM equipped with EDS software capabilities. You can also do other instrumental techniques as well. TOF sims or microprobe analysis are very common to see. The next very important part is stress profiles. So the main thing, so you exchange your glass, you want to know how much stress is in it. This is all based on photoelasticity and birefringence. So this is an extremely common instrument called an FSM 6000, I believe, produced by a company in Japan that allows you to actually view the compression lines within the glass, both in single ion exchange and double ion exchange. There's also other equipment you can use. This is called a scalp, which does the similar sort of thing, but instead it also uses a laser to determine the birefringence of the glass. There's also other methods as well. These are the main two quick ones. And important to those, you also have these stress equations, so very long. This one is used to determine the stress based on the concentration profile as well as the strain that goes along with it. This R function here in the middle, it was related to the relaxation, and then this B up here is something known as the network dilation term. And then this E is just the Young's modulus, and then V is the Poisson's ratio as well. B, in this case, is related to the change in the molar volume. So once you do that exchange, you're changing the molar volume, and then that will go into how the stress is formed throughout the glass. Now, there's also non-traditional ion exchange methods and concepts. So those include the specialties I was talking about. So you have electric field assistance, microwave assistance, ultrasonic assistance. These methods all use an external field to influence the exchange process. In addition, there's non-traditional things like steam or dealkalization, as well as crystallization. So for electric field assistance, you can usually get 15 microns in 5 minutes. If you recall, a normal soda-lime silicate glass usually takes 24 hours to go 40 or 50 microns. So this is much, much quicker. You also get a different style of a stress profile here. So the challenge here is that you can actually end up putting in too many ions in your glass with the electric field, and that can cause it to break. In addition, it's usually only applicable to one side of the glass unless you do an electric field the other way. After that, there's also microwave assistance. So this is actually one of the quickest ones I know of. It's 80 microns in 30 minutes. The issue here is you can actually cause thermal runaway into your glass because the glass is heated volumetrically instead of externally. And then you can have emissivity decrease, and then that can cause thermal runaway. Again, here, this is in a aluminosilicate glass versus conventional versus microwave. You get a much quicker exchange. The last assisted one is ultrasonic, so you can go 32 microns in 3.6 hours. The issue here is that the ultrasonic waves will actually cause a greater increase in the stress relaxation. And there's also the idea of dealkalization. So like we saw yesterday with the bioglasses, the ions can come out of the glass, and you can form a low alkali surface layer, and that layer usually has a lower coefficient of thermal expansion, and you can get strengthening that way in addition. Also in bottle glass industry, they use tetrachloride here, or not tetrachloride, tin chloride, as well as HCl or H2SO4 to remove some alkali from that surface. In addition, recently there's been work done by people at Corning that uses steam or just water, and then under high pressure, you can have molecular water inserted into the glass structure that breaks down into OH groups, and then you can also, once that cools down, some of those OH groups recombine and form molecular water that then expands the glass structure and then forms that compressive stress. This is crystallization. So in addition to doing that strengthening, if you do a certain ion bath and you have a certain composition, you can actually form a crystallization layer on the surface of that glass. More specifically, the most specific example of this is a glass developed by Corning, a sodium aluminum silicate glass where you do a lithium exchange at 860 C, and then you actually form a beta eucryptite crystal layer on the surface, and then that will cause that compression, or that will cause compression via the fact that that crystallization layer has a lower coefficient of thermal expansion. I went ahead and attempted to redo this same glass composition, and this is my example, or this is my XRD of that glass. So just a simple XRD spectra. So you have that beta eucryptite phase showing up after I did that exchange. Another important factor about ion exchange is the fact that there's pre-existing flaws in your glass. We all know that pristine glass surfaces will always have a higher strength. However, it's hard to make pristine glass surfaces, so we always have pre-existing flaws in that glass. The ion exchange medium can actually penetrate those flaws and change the outcome or the strength of the glasses. Oops. It's overlaid there, but another important part, talking about pre-existing flaws, is the fact about sample preparation. So usually if you're doing research on ion exchange glasses, you're going to want to do, you're going to want to polish that sample down to a micron and then properly anneal that glass as well, because the residual stress in the glasses can affect the exchange. Then back to the pre-existing flaws. So I've done some work on how the fact that after an ion exchange bath, that crack or that glass medium can actually end up closing that crack opening. So this is indentation cracks, and the left graph here or left image is before a 1 hour exchange, where I went and used the SEM to measure the crack width here, which is 745 nanometers. After a simple hour exchange in a potassium bath, that crack closed down to 239 nanometers. Now, the main idea here is, sure, the crack is closing up here, but what is it doing at the crack front? And that's something that I don't think many people have looked at. So in summary, the ion exchange process can be used to strengthen, color, and control properties of the glasses. It can also, the geometry is not limited unless you use an external field applied. So if you remember that tempered glass usually has to be flat. If you use ion exchange process, you can usually do all geometries of shapes. So you can do bottles, you can do curved glass, etc. Using those external fields then restricts your geometry again. Any composition may be ion exchange. The effects may not be optimal. And then you should consider the ion source, the time and temperature, as well as the method if you're going to do ion exchange on some of your glasses. And in principles, the strengthening comes from a compressive layer at the surface of your glass. And then the simple picture of a large ion substituting a smaller ion 1-to-1 to induce that compressive strength, except, well, that's for Ben to explain. But I appreciate you listening to me for a couple minutes.
Perfect. Thanks, Jacob. Yeah, so I'd just like to take about the next 10 minutes or less to go through some examples of studies that have showed where that simple model of just a larger ion swapping for a smaller ion doesn't seem to apply, or it breaks down. At least it's a little bit more complicated. The first example I'd like to show with you, this is a soda lime silicate, where we have a silver for sodium exchange. And of course, those environments around those alkali elements or the mobile ions that you're putting in your glass is rather critical to building up a lot of compressive stress at the front of your glass. Engineering those stress profiles is really dependent on what's going on at the local scale around those elements, and how much we can actually understand it dictates how much we can control it. This is some data XAFS analysis, which basically is a element-sensitive technique that allows us to look at the coordination shell around a specific element. In this case, this is sodium KH XAFS. These peak right in the middle is the first coordination sphere, basically the sodium oxygen, and then you can sometimes get a second and third shell as shown here. From this analysis, you can look at the radial distribution and determine the bond lengths, and if you integrate that, you can get the coordination numbers. So here's a nice sodium disilicate crystal that has a coordination of 5. You can see quite nice broad peaks here, and a nice big shoulder, and the background here is a little wiggly. The base glass, the base SLS is this spectrum here, and then you have a little bit of exchange, and then about 40% exchange glass at the bottom here. And you can see that this second shell, and even the first shell, changes quite dramatically. When they quantified that and looked at the changing sodium coordination, a similar composition crystal, this disilicate, had a coordination of 5. The base glass started with approximately the same, about 5. But once they started exchanging, this coordination number started dropping, and the sodium-oxygen distance decrease substantially. For those of you who love spectroscopy, you'll notice that this big, broad first coordination shell peak gets quite a bit thinner and well-defined. So that's interesting that the sodium coordination changes occurring. It's a little bit unexpected. And I show this because this brought to my mind that perhaps those sodiums that are in higher coordinated sites are actually easier to take out of the glass and will substitute for the silver first. And the smaller sites that have a little bit tighter geometry are kept in the glass a little bit longer. This study also so this study is from 1997 over here, Dubel et al. The silver KH XSAFs, they weren't able to extract the coordination numbers, but they did look at the oxygen-silver distance and the the second coordination shell around the silver. What they found is that basically, whether it's a little bit exchanged here at 6% or 80%, the second shell didn't really change. On the other hand, the silver oxygen radius started to increase quite dramatically. And they attributed this in the study to the fact that the silver is a little bit more covalently bonded and is able to interact with those oxygens and pull away some of that electron density to loosen it up. The next study is a similar exchange, silver for sodium, but on a sodium aluminosilicate here. And there's some questions about the property data earlier. So in this study, they have about 20% sodium, 10% aluminum, and 70% silica. The TG data is at the top here, and the coefficient of thermal expansion is at the bottom. They seem to show a kink around 50% sodium substituted for, 50% silver substituted for sodium, whereas the thermal expansion just continually decreased as you increase the silver content. When they looked at the Raman in this case, you guys are all familiar with these plots now, they saw massive changes here in this band around 1,000 inverse centimeters here. It completely grew. So this is the silver-free base glass, and this is the 100% substituted silver for sodium. And you can see a massive change in the Raman spectra towards shifting towards lower Raman shift. Obviously, something quite dramatic is happening in this glass. For me, that's quite a signature of depolymerization reactions occurring. But the authors didn't seem to actually discuss this in their paper. They noted it. They said, wow, there's pretty massive changes going on, but we'll leave it at that. The only inferences that they brought were, or the main inferences that they got out of this study, was actually that the silver tends to swap for the sodium that are sitting by lots of MBOs first in this early stage. And then after the 50% mark, they said, oh, these silver are now substituting for the sodium that's sitting to charge compensate an aluminum tetrahedron. And they said there was actually a site preference in the substitution process. But that, as I said, that massive change in the Raman signature indicates to me that something more strong is going on. So I looked at this a little further. Those were a couple older studies. More recently, back in 2014, Gao et al. And the folks from Corning, they published these results, and they looked at different potassium alkali aluminosilicate glasses, and they put them in a salt bath of the same ion that was in the glass. So they put a lithium aluminosilicate in a lithium bath, a potassium aluminosilicate in a potassium bath, and they got some very interesting results. One of the key results was around the oddity that is the potassium behavior. When they measure the fresh glass here, they got this profile, and in the outer 1 micron, so this is the edge of the glass, and we're going down in depth, and this is the concentration of potassium in the unexchanged glass here. They showed that the potassium seems to be, depleted in the outer micron, 1.3 microns of the glass, but when they did the exchange, that profile shifted right out as one might expect. They looked at this a little bit further, and they noted that these effects are not shown in lithium, and the effect is quite subtle in sodium. But they also they used SIMS to look at the water in here. So this is the hydrogen content of the glass, again as a function of depth going from the outer surface and inwards. And here is the inset is the lithium glass. Here's the red curve is the sodium glass, and the blue curve is the potassium. And they show that there's almost no depletion at the surface of the lithium glass. There's a 1.4 or so micron depth penetration of hydrogen. There's 1.4 micron penetration of hydrogen into the sodium depth, into the sodium aluminosilicate, but there's a massive 3 micron penetration of this water into the potassium-bearing glasses. So something about potassium seems to be adding water to the mix and obviously showing a pretty strong influence. At the end of the day, these are only a few microns, and whether this actually affects the final strengthening of the ion exchange glass, I don't know. I haven't done enough studies. But these are certainly something to think about, because one of the most common ion exchanges we do is that potassium for a smaller alkali element. More recent study, just from last year, from Belostovsky, in a little bit complex but alkali calcium lime silicate. This is Auger spectroscopy, so Auger emission spectroscopy, quite a surface sensitive technique. And they did several line scans from the edge of the glass inwards. I've blocked out all the mess that is out here that comes from just artifacts of the spectroscopic technique. And I want to focus on the actual penetration depth. There's 3 concentration profiles in this glass, and sorry for folks that don't like the squiggles, but there's a calcium content here, whose concentration in from the ion exchange front remains relatively constant as you go in, deeper into 45 microns into the glass. And then if you look at the potassium and the oxygen, you see that our potassium exchange increases that potassium at the surface, and it decreases as you go into the bulk. Now that's all as we would expect, except for the fact that the oxygen is changing as well. We seem to have a big increase in the oxygen content alongside the potassium. Is this related to water? I don't know. But the authors infer that there's enough strain put on the local bonds from the volumetric change from the potassium for sodium that you will actually break up the bridging oxygens to produce a underbonded silicon and an MBO here. They did some calculations of the strain effects related to different coordination changes, and they suggested that these defects may even involve peroxyl radicals, O2 molecules sitting as interstitial species within the glass, and peroxyl linkages in here. Moving back a little bit further in time, but some more studies to go back to this idea that depolymerization may be evolving in the network along with ion exchange, and showing that last result where the oxygen concentration is actually changing along with this process. I want to show a few last examples real quick. This is a classic study by Tomozawa's group from RPI back in 1997. They did reflectance FTIR on an exchange below TG, so there's a potassium for sodium exchange in SLS. And they show below TG, there's very subtle changes, but a very distinct shoulder here around 950 developing. Again, this is another signature of maybe some depolymerization is happening, or something else is going on at least with this glass during the ion exchange process. When they did the same measurement but above the glass TG, this became much more pronounced. They had a massive increase in the peak here, which I think is a clear sign that polymerization reactions are part of this process as well. Last study I'd like to highlight is this study from 2014 in a sodium aluminosilicate glass with a little bit of zirconium in there. You can see the outer surface and the depth into the pristine glass here in the bulk. You see massive changes in these shoulders. The relative intensities of the 980 and the 1070 peak here are clearly changing as a function of the substitution depth. The way they did their analysis, they came to the conclusion that basically as a function of depth, there's no change in the Q4, but there's an increase in the Q2 at the increase in the Q3 at the expense of Q2. The reason I show this example is to make a nice point about structure, and that is unfortunately they interpreted everything in terms of disproportionation, where a Q2 plus a Q4 react to form two Q3s. But of course, the Q4 is constant here, so it can't be involved in this reaction. So I want to make a point about the distinction between depolymerization and disproportionation, because it's really, I think, really important and fundamental to unresolving some of the confusion in some of the ideas. For those of you who've read some structural papers, you might have come across scratching your head. And part of the problem is that there's frequent papers, even until today, that mix up these concepts. When you have a bridging oxygen and you add a modifier oxide to it, you're adding oxygen to the system. And you can react these to form two non-bridging oxygen. You can break open a bridge, and you add another oxygen onto one tetrahedron, you have two non-bridging oxygens in it. For those who are a little familiar with the chemical way of writing it, you can add, for example, my favorite element, one of my favorite elements, barium oxide to silica, and you produce, in this case, a metasilicate that's charge balanced by this barium ion sitting nearby. If you're a structural person and you've lived for the QN species of all the talks this week, this QN, 2QN plus a barium oxide will convert to 2QN minus 1. Okay? So if you're changing not just the alkali content, but if you're changing the amount of oxygen in the system, you are talking about depolymerization or polymerization reactions. You're not talking about the other thing, which is disproportionation. This is similar to the example we just showed, but 2QN can be converted to QN, where N is the number of bridging oxygens, so you have one less bridging oxygen and one more bridging oxygen. And there's some examples here. For example, 2 Q3s can go to a Q4 plus Q2, and so on down the list. In these cases, if you count up the bridging oxygen and non-bridging oxygens on either side of these reactions, the BRIO and MBO don't change. So if you actually want to change the proportion of BO, you are talking about depolymerization over here. If you're not, this disproportionation reaction, it just cannot change, whoops. It cannot change the proportion of bridging to non-bridging oxygen ratios. Okay? But it absolutely can change the distribution of the QN species in your system. And that's what makes these things a little bit tied together and a little bit confusing. So I'll leave you now with a few last points. First of all, that in addition to everything Jacob showed you, there are many structural probes to look at these on a fine spatial scale and get at some information around what's happening structurally behind these things. Many studies have showed and repeatedly showed different data sets with completely different techniques on completely different glasses that I believe show this depolymerization reactions being quite important in the ion exchange, and that may also involve water as well. And the final part of it is that if we want to engineer the stress profiles to optimize the strength of these glasses, we probably need to go a step further and go beyond this simple swap model and get into some of the structural details. But there's far too few studies that quantify that appropriately. So, muito obrigado. Thank you very much. And
Thank you very much, Jacob and Ben. All right, let me start with one question to Jacob. You mentioned that some compositions can be designed to relax less during the exchange process. So could you please dwell a little bit more and expand a little bit more on this?
I can't expand too much, but I can expand a little bit. There's certain specific compositions that will allow you to relax less based on if they have, for instance, I believe, I think, let's see, whether or not there's certain, I think the difference in, I think it might be the boron coordination or other structural compositional effects that can have or be in the glass. I know develop-wise, more broadly, is that I believe John Morrow and others have modeled specific compositions to look at the minimization of those stresses. Otherwise, I don't know any more specific composition-wise, but I know that they exist.
All right. Questions? Francisco.
In soda-lime glass, for example, you may have these alkali channels
Yep.
inside the structure. What's the contribution of them, or no contribution at all, for ion exchange? Are there any?
Yeah, so there's, what he's talking about is I know in the modified random network, or you'll have ion channels that are specifically where you have a grouping of ions and then surrounded by the bridging oxygen. In those cases, it'll probably be slightly more efficient, as those sites are probably more similar to the exchanging ion or incoming ions that allow them to swap out in place as well.
If I can expand a little bit on that. So that's how Bill and I got into trouble together, because he had published this paper way back when on transitional states, where he showed that there's a difference between a random network, where the random network transitions to a modified random network. And take this as very tentative, I am not saying this with a high degree of certainty, but where you have the transition to the modified random network is probably where you're starting to get those channels. And it seems to be, from talking to Bill, that the diffusion rates are much faster and able to go much deeper when you're in that modified portion. But in that transition region, you also do have some very interesting behavior. So depending on where you are in the completely random or completely modified random, actually does control the diffusion profile and the time and the effects of the field assists that Jacob was talking about.
Okay, thank you. Can you go back to your depth profile page? Maybe many pages before.
Which one?
Yeah, depth profile. It's pretty early. You show,
This one?
No, not this one. The DOL file. You mentioned the LCM measurement. Go
There's
down.
also this one.
Go
Or are you
down.
talking about like the concentration profiles I have?
No. You measure here.
These ones?
20, yeah.
So
My
these aren't stress profiles. These are
Yeah, maybe the 18 is better. 18.
18.
Page 18.
Yeah. Yep. So these.
My question is, in this profile, why is the maximum, the highest potassium and sodium ions not started from very surface? It always be like several hundred nanometers.
Nanometers. Yeah. So there's I believe there's what he's asking is, why is there a peak a couple microns in, and the peak doesn't start at the surface, right? Is that what you're asking? There's a couple reasons why. So I think one of them can be due to the fact of how I did this sample measurement. So if I am off in doing the analysis a couple microns from the edge of the sample, that can cause that. In addition, I think there's also exchanging that's occurring during that surface as well, depending on how long I have done this for. So I exchanged it for 24 hours so I can have back diffusion from my concentration gradient as well from the salt bath.
In fact, when I did my exchange maybe several years before, I always see this kind of profile.
Yeah, where you have
it's
a
so
step
confused
and then-
why
yeah.
why is when we study, we measure the land scan, we use the ICM land scan from the very surface.
Yeah. So
it always show like this with different samples.
Yeah.
Many samples.
Yeah, so these are all mappings. So
Yeah.
I do the EDS map, and then I'll take the average, and I'll find that.
Okay.
But there's a couple reasons why that occurs. So I can also talk to you later too about it.
Okay. One more question.
Yeah.
You mentioned that you use the steam as an ion source.
Yeah, so there's
steam.
Corning has done ion exchange via steam.
Yeah, my question is, the steam comes from the solution with water, and that such high temperature isn't possible to how to say make some corrosion of the glass surface.
Like corrosion of the glass surface.
Corrosion of the glass surface.
So-
because high temperature and the water.
I have to read the paper, I can send you the paper too. But what they do is they would do a couple droplets of water inside a furnace, and then that brings it to a high pressure or high steam pressure, and that water is actually exchanging with potassium out of the surface. So it's not so much corrosion.
Okay. Okay,
yep.
I understand. Okay, thank you.
Yeah, hello. Thank you, Jacobs and Ben. So when you talked about electric field assisted ion change, how do you do it?
So, yeah.
Which direction you apply the field?
Yeah, so they're asking how you apply or how, like what the process or setup looks like for an ion exchange setup. There's a couple different ways you can do it. You can do it with paste, like I showed you, or with paste and then two electrodes. So you can have your glass in the middle and then a cathode and an anode on both sides. You can also do it, I've seen studies where they've taken a test tube and they submerge the whole test tube or the whole test piece. It's usually a test tube into a salt bath, and then you use platinum electrodes on both sides, and then you can apply a field that way, and then you can reverse that field through electronics as well. But you can do the electric field both ways if you reverse the field.
Because in my mind, let's see if silver, when you push silvers to the glass, so you do not exchange because there is no reason for the potassium to go out. You understand what I mean?
So you can, usually you're exchanging, so if your glass is here, you're exchanging, you're pushing potassium in through the glass, so you're pushing those silver ions further into the glass as well. And then if you reverse it, you have the opposite direction from the opposite side.
Thank you for the presentation. I would like to know how do you account for stress-induced changes due to diffusion coefficient, maybe because of mismatch in ionic radii, probably during modifying the glass surface.
So you're asking how does one account for the network dilation?
My question is, during ionic exchange,
Yep.
when trying to modify the glass surface, how do you account for the stress-induced changes in diffusion coefficient due to mismatch in ionic radii?
Oh, so I think I understand now. So, like, how do you account for the fact that you're increasing a stress profile in the glass?
Yeah.
So the first thing is that obviously you want to form that stress in the glass, but there's also when you're doing an exchange, if you're doing an exchange, usually bigger ions will always go to a tensile stress area if it's present in the glass, and then the smaller the smaller ions will go to a compressive stress to relieve, so they counterbalance during the exchange. So when you do an exchange, you'll have a compression layer. After that compression layer, you'll have a tension layer. So if you were to do that exchange and then, say, do a heat treatment, you'll see that the exchanged ion will go further into the glass to relieve that tensile stress, and then you'll get, like what I showed, a back diffusion, where that smaller ion will then go towards the surface to relieve the compression. That make sense?
All right. Hi, Ben. Can you go to the slide where you show the Hammond changes, the QN species changing? So my question is related to the Q4 that you said that's constant. Do you believe that it can be changing and doesn't the people didn't, because this is from fits, right? And I don't know why, but normally people don't show the fits. So looking at the data, do you believe that there are some possibility that the Q4 is changing?
Sure. Sorry. Yes. So Stratos Commitsis was involved in this paper, and I know that he absolutely knows this. I put this example here as an excuse to talk about the distinction between polymerization and disproportionation. because it's so commonly confused and because it obviously seems to be part of the story here. Okay, so when you look at the details of this paper, I wouldn't look too closely. There's other better examples of this, such as the ones I showed. So no, I can't tell you from the data there whether that is absolutely true. And remember that those are relative relative intensities, not absolute concentrations. So there is also another factor in here that's not completely taken account for. But again, I use this for educational purposes, not this is how I would do my curve fitting. Okay?
Right, thank you.
Okay, well, I think now we have to go downstairs. There's a poster session now. We have the opportunity to visit the students' posters and then be back at 4:25, please. 4:25. So we have a long break, but that's on purpose because of the poster session. 4:25 sharp to start the online lecture directly from Istanbul, 6 hours ahead of us. Thank you very much again, guys, for your great lecture. Oh, somebody lost some money, you know. Oh, some money was found here. 200 reais, 250, 300 reais. Well, I'll be a rich man then. It was here. It was here. Huh? Ah, okay.
Som, som. Alô, alô. Testando som 1, 2. Testando som 1, 2. Alô, alô.
Hi, Banu. Can you hear us, Banu?
Yeah. Can you
Oh,
hear me?
Hi, we can hear you.
Ah, okay,
oh,
okay then. I can hear you also. Okay.
very good.
Hi,
How
hi.
are you? How are you?
Thank you, thank you. And you?
We are fine here. What time is it now for you?
Now it is 10:30 p.m.
10:30.
Almost
Poor
at night.
Banu.
Yeah.
I apologize. I really apologize.
Ah, no
Really
problem, no
apologize to
problem.
give you this terrible time.
But she looks very fresh for 10:30.
She does. She does. She looks very fresh.
Yeah.
Yeah.
Yeah. After
Uh,
the presentation, I can sleep.
yeah. So, how long do you think you need for your lecture? How many minutes you need?
I think 20 minutes is okay for me.
20 minutes. 20 minutes.
Yes.
Fantastic, fantastic. So let's do it in 20 minutes. Then maybe some people will ask questions, maybe 10,
Okay.
15 minutes. It depends on the profile of the guys here. But great, great.
Yeah, okay.
So I just ask you to wait a little bit before they return from the coffee break. I always have a very, very hard time to fish them downstairs from the coffee break and to come here. But please,
Yeah, I can imagine.
Okay.
can shot, and I'm going to collect everybody
Okay.
to come here. Okay?
Nasılsınız Banu Hanım?
İyi canım, sen nasılsın?
İyiyim ben de. Şimdi öğrencileri toplayıp gelecekmiş de orada birazcık
Tamam,
bekleyeceğiz mecbur.
tamam, tamam. Şirin, sesim kesilmeden geliyor mu?
Evet ben duyuyorum sizi çok rahat. Bütün salon duyuyor. Gayet
Ha,
güzel
tamam.
geliyor.
Böyle biraz bağlantım sanki arada kopuyormuş gibi geliyor ama tamam, umarım bir
Ha.
sorun olmaz. Tamam,
Duyuyoruz sizi şu anda.
tamam.
Okay, now we have a critical mass here. We have a critical mass. It's a great pleasure and honor inviting a very distinguished researcher from CICEJAM. CICEJAM is a very large company in Europe. The headquarters is in Istanbul, but they have plants in different countries, in several different countries, and they produce a lot of different types of glass, including very nice wine glasses which are chemically strengthened. You can buy those in the market. They're beautiful. What's the trade name of those glasses? I've forgotten the trade name of the chemically strengthened. Stem Zero. Stem Zero. Look at the internet for it. Stem Zero
yes.
glasses. They're very, very nice. With extremely fine walls and very resistant to fracture. So in their research center, they have about 200 people, 200 researchers, very brand new with all equipment. So CICEJAM is a great company, and it's my pleasure to host here Dr. Banu Arslan for her lecture. Thank you very much, Banu.
Thank you, Professor, for your kind introduction. I can share the screen. Yes. And can you see my screen now?
We can see if you, yes, great, perfect.
Yeah, yes, yes. Okay, then thank you for the nice introduction to CICEJAM and also to me. Actually, this is Banu Arslan. I'm Advanced Glass and Melting Technologies Manager for CICEJAM. I have been working there for about 15 years. Today, actually, I will be giving a presentation that provides an overview of CICEJAM's perspective on cullet, highlighting key aspects of its approach, how it conducts related studies, and the projects it is involved in. Rather than a lecture, this session aims to raise awareness about the topic while also sharing fundamental insights into CICEJAM's strategy, actually. And additionally, I will discuss how CICEJAM addresses the challenges of cullet availability, particularly in countries like Turkey, where access to cullet is significantly limited. Yeah, so as an introduction, let's talk about who is CICEJAM at first. CICEJAM is currently one of the world's leading glass producers with production operations located in 14 countries with 25 plants and with 24,000 employees. We're producing almost 6 million tons of glass and 5 million tons of chemicals and 4.5 million tons of raw materials annually. We are doing sales in over 1,500 countries around the world, and our headquarters and R&D center is located in Turkey, in Istanbul. Let's move on. Actually, CICEJAM is only a global producer operating in all main key areas of the global glass industry. As Zanato said, flat glass, glassware, glass packaging, automotive, and also glass fiber. It ranks among the world's top 2 producers in glassware. And for the look at the laser. Yeah. And among type 5 producer in glass packaging and also for the flat glass. And Şişecam is also world's one of the top 2 largest producers of soda ash and the world leader in chromium chemicals. And lastly, some words about our R&D activities where I am working in. Şişecam is the first company in Turkey to lay the foundations in corporate R&D culture in 1976. Today, our R&D center is one of the largest and well-equipped R&D center in Europe in glass science and technology. The center has 31 different specialized laboratories ranging from basic research to laboratory scale pilot manufacturing trials. We have also regional R&D laboratories next to our production facilities, both in Turkey and in many countries like Bulgaria, Italy, Russia, India, and so on. We have state-of-art equipments, modeling and simulation tools, and advanced characterization techniques to ensure operational excellence, to design, optimize, and develop special compositions, and to develop value-added coated glass products. We have a team, almost 280 researchers. 38% of them is women, with 10% of PhD. As Şişecam R&D team, we are active in all main production activities of Şişecam, actually, namely flat glass, glass packaging, glassware, and glass fiber. And our competencies are mainly on melting technologies, glass and refractory materials, coating, and also surface technologies. Yeah. And yeah, as Şişecam, actually we aim to contribute to a better world in different areas through our sustainability strategies based on 3 pillars. Protect the planet, empower the society, and transform life, and take care to carry out all activities in accordance with these pillars. Today, I will talk mainly on the first pillar, protect the planet. Yes, and as you all know, in order to make glass products, we introduce batch materials into big tank furnaces. And actually, the energy is supplied by the natural gas and electricity to reach pretty high temperatures, as you know. Due to batch reactions and combustion of fossil fuels, this process produces a great amount of carbon dioxide. Approximate numbers for the breakdown of the given elements can be given as 1,500 meters of glass produced and correspondingly 95 of carbon dioxide emitted annually. Contribution portions is roughly given as 1/3 for the decomposition reactions of the raw materials, and 2/3 is combustion of fossil fuels related emissions. These are main pillars where things are changing. First, there's a big move towards green fuels, as you know, and this means the industry is starting to use energy that is cleaner and doesn't destroy our planet. There are lots of projects going into using more renewable energy like wind and solar power. And there is a big push to use green hydrogen too, which is a cleaner fuel option. The idea is to create an ecosystem via hydrogen valleys, where everyone from the makers to the users works together in a clean energy environment. And the second, the technology leaders are working on new ways to melt glass that are better for the environment. We are trying to use more electricity in a smart way, design new types of furnaces that are less polluting, and find ways to capture the carbon emissions before they harm the air. And the third one is about the decarbonated raw materials, innovative batching systems, and also introduce low carbon glass products and recycled glass. Yeah, let's take a look at the properties of glass as a material. Although the glass industry is responsible for high carbon dioxide emissions, the final product, glass, is a 100% recyclable material that contributes to reducing these emissions. This makes it an incredibly sustainable material. As the most sustainable packaging option available, it is also an excellent example of the circular economy in action. Recycled glass plays a pivotal role in sustainable glass production. Its ability to be endlessly recycled without compromising quality makes it is an essential material for the future. I also would like to briefly mention the following points. In recent years, in line with Şişecam's sustainability goals, to produce more environmentally friendly products by increasing the amount of cullets a subject, this is a growing importance. The use of cullets in glass production offers substantial benefits, including raw material conservation, enhanced energy efficiency, and a reduced environmental footprint. These advantages align with sustainability goals of Şişecam. In glass production, we use cullet. The use of cullet actually presents several challenges that need to be addressed to ensure the quality and efficiency of the manufacturing process. Let's have a look at the key limitations and considerations when incorporating cullet into glass production. Firstly, the availability of cullets can vary significantly depending on location, affecting the consistency and reliability of its supply. And secondly, cullets can exhibit in differences in composition, color, and redox conditions, which can impact the quality of the final glass products. And thirdly, it is crucial to remove contaminants such as ceramics, glass ceramics, ferrous and non-ferrous metals, and organic components to prevent the defects in the glass. In addition, the level of the heavy metals within the cullet must comply with regulatory limits to ensure the safety and environmental standards of glass products. And finally, the grain size. The grain size of the cullet must match the specifications of required glass production to avoid refractory corrosions also. Yeah, It is crucial to consider how scientific approaches should be structured in all studies conducted within this concept. I would like to share with you how we in R&D Center handle our studies in this context. Yes, the journey of cullets from raw materials to final products involves several critical stages. I will guide you through the comprehensive process, highlighting key phases, their significance in transforming recycled glass into high quality end products. Characterization of raw materials. Yes, detailed analysis of cullet characteristics to determine suitability and quality of glass products. And lab-scale experimental studies. These studies are conducted to understand how cullet influences the melting process and also the fining process, and ensuring also optimal glass quality. And the characterization of lab-scale samples. For that case, the lab-produced glass samples we examine the optical properties and also the potential glass defects in the lab-scale materials. And also the pilot scale studies. These studies are also to simulate actual production conditions, addressing any issues and validating lab-scale findings. And finally, the end product, production at the plant. Yes, here, full-scale production of glass products incorporating cullets, ensuring they meet all quality and also performance standards. By meticulously analyzing and optimizing each phase, we can achieve sustainable and high-quality glass manufacturing. Yeah, the first step, the characterization of cullet and glass samples, is essential for ensuring quality and consistency in glass production. By using advanced methods such as microscopy, particle size analysis, SEM-EDS, XRF, and heavy metal analysis, we can achieve a comprehensive understanding of the material properties, leading to improved glass production processes and products. And the second step, to ensure the high quality of our products, lab-scale testing of cullets. We do pot melting tests, which are shown in the top right images. These tests are conducted at high temperatures to simulate manufacturing conditions. We carefully monitor the batch free time and bubble free time, which are crucial parameters in the melting process. And the bottom right image, highlighting our advanced melt monitoring and gas detection process. These ensure that the melt is homogeneous and free from defects. We observe foam behavior of the batch and the gas content is within the required specifications. By maintaining a strict control at each step, we can achieve consistency and excellence the product quality, actually. Yes. And after the melting tests, the impact of cullet on glass color is examined. It is important to understand how the content and usage ratio of glass cullet affect the color of the final glass products. One example is in the slides, comparative data showing changes in glass color from 2021 to 2022, actually, here, illustrating the impact of varying colored content. On the right side, you can see the mini-melter system, which is capable of producing 10 kilogram of glass, enabling the creation of prototype samples. Yeah, like that. With this system, we can generate preliminary data on potential outcomes in a real furnace. And in addition, we can simulate and analyze real production conditions to identify and mitigate issues before full-scale production. By truly investigating the effect of colors on glass color and conducting pilot trials, we can optimize glass production processes and ensure high quality, consistent end products. These steps are essential for translating laboratory findings into real-world manufacturing success. The integration of material science and advanced experimental studies pivotal in driving forward scientific discoveries in glass production. In this slide, I will share how we approach color studies and colored studies and illustrate the journey of Şişecam's first product made from 100% recycled glass cullets, from initial research to the final product. This slide covers the highlights key scientific discoveries and innovations in glass production, focusing on the interdisciplinary synergy of material science and advanced experimental studies. Let's see what we have done while developing these products. The first thing is determining how different factors influence the color and optical properties of glass. And secondly, studying the effect of colors on melting efficiency and finding behaviors to enhance glass quality. Observing foaming behaviors using high temperature observation system to prevent defects. And fourthly, conducting a scale-up studies up to 10 kilogram, as I said in the previous slide, glass-colored prototype samples. And the fifth is scaling up from lab experiments to pilot production in a handmade plant in Denizli, in Turkey again, to validate findings. And finally, the sixth one is ensuring the end product meets criteria for chemical homogeneity, optical parameters, durability, and also the mechanical properties. And finally, securing IP rights for new discoveries and innovations in glass production. Yeah, let's have a look at more detail in our 100% recycled products. As Şişecam, certain amount of recycled glass is always used in our glass batches actually, but there are some challenges of using glass cullets for the industry. Collecting the glass cullets, sorting it, cleaning it, and the use and one of the biggest challenge is fine cullets. That means smaller particles cannot be used in the production. Actually, I will mention the reason in my next slides. On the other hand, despite all these challenges, we have developed a special product. Şişecam's recycled glassware product is made from 100% recycled glass. Used cullet in the production is previously used at least once, actually. Almost 40% reduction in carbon dioxide emissions was achieved with this product, as well as energy saving of 30% can be achieved also. In this product, phosphorus blue color was developed with R&D studies and transferred to production for color stability, recycled color ratio of different sources, but as adjusted according to iron content. Mostly recycled glass products in market contains many gas inclusions and bubbles. We have changed the consumer perception in this direction, actually, and we have introduced a transparent and bubble-free recycled glass to the market for the first time. In summary, Şişecam has brought together its awareness of environmental responsibility, advanced production skills in this glass product. And also, we involved in an emerald green bottle project. This study focuses on the 95% utilization of recycled glass in the production of emerald green glass bottles, aiming for sustainable and efficient glass packaging solutions. Specifically for this project, we have carried out experimental studies specific to the target color from a mixture of glass colors containing different colors in flat glass and glass packaging and shared with the customers. The integration of 95% colored in emerald green glass packaging production presents significant sustainability benefits, but also poses challenges related to the material supply and quality consistency. Addressing these challenges through advanced analytical techniques and optimized process is crucial for successful implementation. And let's look at another study which investigates the feasibility and challenges of using 100% recycled glass colored in flat glass production. This trial was conducted using 100% colored for a continuous period of 2 weeks, utilizing internal colors again. There may be some limitation, mostly due to color and composition, because high quality production is expected in terms of optical performance. And secondly, when colored with appropriate composition for production is identified, the colored ratio can be increased to 100%. It is necessary to ensure the feasibility of high tonnage production for the architectural and automotive glass sectors. Yes, and as I mentioned in my previous slides, the supply of glass colored varies significantly depending on the location and also consequently, utilizing high quantities of colored in the glass production becomes challenging due to supply issues. Additionally, some of the available glass colors consist of fine particles. These fine particles can cause carryover problems in the furnace, leading to adherence to refractories, resulting in refractory corrosion and reduced furnace lifespan. Therefore, the inability to use the fine particles of already scarce colored further restricts its utilization actually. In particular, due to supply bottlenecks in Turkey, despite all these drawbacks, there are occasional requests to evaluate the use of fine particle colors. On this slide, actually, we can see some of the requests we have received over the past 2 years for this purpose. Yes. Actually, during the cleaning process of cullets, there are some breakages in collection, and around 10% is broken into smaller particles, typically smaller than 4 millimeters. Due to the reason that I have mentioned in my previous slide, around 10% of cullets can never be recovered because of the refractory corrosion. We have embarked on a collaborative project to achieve full recyclability of collected glass by developing a method to produce remeltable briquettes from smaller particles, which can be safely used in the furnace to make new glass products. We also proved the melting advantage of briquettes observing with high temperature melting observation system. It shows similar foam thickness with the reference batch, which doesn't contain smaller cullets, and one advantage was less bubble formation. Therefore, briquetting of cullet offers significant operational and melting advantages, contributing to more efficient and sustainable glass production. Addressing the challenges related to mechanical strength, chemical preservation, binder selection, and impurity management is essential for optimizing this process, of course. And recycling and reuse of glass materials are crucial for sustainable production. Let's have a look at the recycling potentials of PV panels, solar glass, and also laminated glass, which are able to boost the usage of the glass cullet as well. As you know, although laminated glass cullet needs to be separated before use, and it is preferred for flat glass production. It can be used in certain proportions in glass packaging production. When we look at the PV panel solar glass, it is not suitable for use as cullet after becoming a PV panel due to containing copper cells and coatings. They require specific modifications to be recycled effectively. While PV panels, solar glass possess recycling challenges, understanding their specific limitations and potential solutions is essential for optimizing their reuse in glass production. With this belief, we decided to take part as a stakeholder in the Horizon Retrieve project, a Europe and initiative in 2024. The Horizon Retrieve project actually aims to develop innovative technologies for efficient recycling and reuse of end-of-life PV panels and focusing on high-value material recovery and sustainability. In this project, Şişecam focuses on firstly the glass recovery from oil panels and utilization of the recycled glass as high-value glass, and secondly, glass recycling to PV quality. At the bottom of the slide, you can see the workflow. As you will see, Şişecam will focus on determining the limitations and characterization of PV panels, as well as identifying the usage rates that will ensure high-quality production. By achieving high separation rates and reusing valuable materials, the project aims to contribute to a circular economy and also reduce environmental impacts. Yes, that is the end of my presentation, and thank you for your patience.
Thank you very much, Banu. It's very relevant for the students to be aware that when you move from your lab, doing your 100-gram melt to tons of kilograms of glass, you have to be aware of the source of raw materials, of pollution, CO2 footprint, refractory corrosion, alternative fuels, you name it, bubbles, bubble removal. In the lab, we don't care so much for these things, but in real life, they deal with very complicated problems. Also, I congratulate you and the team for being able to produce glasses 100% recycled, using 100% of cullet. And they are available at Passabate. They are available for sale, these glass cups.
Yeah.
Very nice. Next time I go to Turkey, I'm going to buy some at Passabate. They have a very nice 2 stores, huge stores in Istanbul. Anyway, just one question from my side, and then see if the students have questions or the other professors.
Yeah.
I always wondered, how can you control the cullet? Because you get cullet from all over the place, and you have shown that it varies from year to year, but not from year to year. It varies from day to day, I guess. These cullets come from different sources. So how is the quality control before, you did your research, etc., but before they go to production, to the production line?
Yeah.
You need a very tight quality control, I guess.
Yes, actually, it is really difficult. At first, I need to say that to determine some chemical compositions, we can control the cullet ratio, the cullet's color, but most of the time, actually, it can be some glass ceramics and also glass ceramics and some non-metallic issues, and actually, we have a cullet factory near by a plant of glass packaging. They can separate not too much actually, but they can separate the color, the glass itself from the ceramics and also the organic materials and so on. But sometimes they can be some impurities for the cullets, so we can see as a defect for the glass production. We cannot actually totally, completely clean the cullets itself.
Okay, thank you. Any question to Dr. Arslan about glass production, cullet use? Leo, please identify yourselves so she would know who is talking to her. 1, 2, okay.
Thank you for your talk. I am Professor Leonardo Gallo from the Federal University of Lavras. And when talking to my students about glass production, specifically when we talk about industrial glass production, in Brazil we have a difficulty recycling glass, specifically because industries do not want to get glasses from other manufacturers to try to keep their compositions in line. And as Professor Edgar told us, there are many problems that can arise. For example, refractory corrosion. How do your company deal with these problems so that they can be minimized? Thank you.
Yeah. Actually, Actually, the most important thing for the refractory corrosion is the fine particles. So we can just eliminate the fine particles as now. Actually, we cannot use them, but we have some studies on that topic to use the fine particles, avoiding the refractory corrosion like briquetting. So this gives a chance to use the fine particles as well for the glass production. But actually, it is of course, it is the price can be higher to use the fine particles as a briquette, but we need to do that. So we have some studies in R&D center. Also, we are planning actually to do some plant trials also for this within this year.
Hi, I'm River Peo from Alfred University. I'm a grad student there. So first off, I think we work with one of your former colleagues, Ejim. Do you remember
Yes,
Ejim?
yes,
Yeah,
yes.
she says hi.
Yeah. Yeah.
And I
Yes,
want to
I
know
know her.
about the what sorting methods you landed on for your cullet, because I know you can use like XRF, or there's even like AI methods now to sort out all the cullet. So I kind of want to know what Sejam landed on.
I cannot follow your question. Could you please repeat it?
What sort of characterization methods did you use for sorting the glass cullet and like getting rid of the contaminants and sorting all the glass colors?
He is asking whether. Okay, you got
Yeah.
it.
Yeah, I got it. Yeah. Actually, as I told before, actually we have a cullet plant nearby a glass packaging company. With an optical sorting, they are just separate the color of the glasses, and also we also before giving the furnace, we also do some chemical analysis to understand how and which amount of proper impurities they can have, and we decided to use them as in the color glass and also as in the colorless glass and so on. Yeah, with some optical measurements methods.
Cool, thank
Okay.
you.
Any other question? Jiwon.
Hello, thank you for your presentation. This is Jihong Zhang from Wuhan University of Technology, China. In your presentation, you mentioned the PV glass cannot be directly used as a cullet for remelting. My question is, why and how to improve the waste PV glass for reuse and some potential product, some kind of potential products. Can you give
Yeah.
some answer?
Yeah. Actually, for the PV glass, actually for the flat glass production, it is limited to use the PV glasses because for in the flat glass production, there are some special glass defects at first. I know that there are some studies to use these PV glasses in the production to make them more useful for the glass production. But now Şişecam doesn't have any study on that topic. Actually, we are just looking for some collaborations to use the PV glasses as a glass, as a cullet, actually, glass cullet, yeah.
Okay, okay, thank you.
There are no,
yeah,
there are no studies on that, yeah.
Okay. In fact, I saw your company does not have some central in China. Please sometime go to China and to make some research or product.
Yeah, yeah.
Okay, thank you.
Thank you. Thank you.
Okay, so I guess we have to thank you. It's very late now in Istanbul, and you deserve a nice rest. And thank you, and thank you, Kai, and all my friends in Sissejan.
Yeah, thank you.
Let's give her
thank you.
a good round of
Thank
applause.
you. It is an honor to host you. Thank you. Thank you.
Thank you. Have a nice night.
Thank you. Bye-bye.
Okay, we have 10 minutes. So you take a break here, not downstairs, because then it's tough to get you back. And we have the final lecture at 17:30. Thank you. One student wanted a book for her supervisor, but I can't remember who are the student. A supervisor's name is Professor Allison. Is she here? Your colleague. Let me speak in Portuguese, it'll be easier. Aquela moça que estava com você ontem, Carlton, a moça que o supervisor foi para Araraquara, too bad, she'll not have the book. So there's another lady on the line. Who's the other lady who wanted a book for her supervisor? Not here. So you have one, Roger. Because your girlfriend asked, you know, she cared for you. She cares for you. This is the last copy. Roger. Valeu. Ele te deve jantar, hein? Hã? Ah, vamos mandar bala então. Põe ele, põe ele. Tá, pode chamar. Yeah, Dr. Satoshi from AGC is already online, so we are going to start to speed up things. Andrea. Você fala, eu passo o microfone para você. Me lembra, vem aqui. Guys, we have to start. Dr. Satoshi is online, so we are going to start. Hi, Satoshi. Can you hear me, Satoshi?
Hi, Edward.
Hey.
I can hear you.
Hi, how are you?
Hi. Good morning.
How are you?
I fine, fine.
Good morning.
To a little bit earlier in the morning in Japan, but no problem. That's
I
good.
apologize.
It's
I
fun.
apologize. I
No,
could.
no, no, no, no.
I could.
You're welcome, and I'm happy to join this school. Thank
Very
you.
good. You know, I could not control this time shift. It's like 12 hours
No, no.
from here to Japan. Tough to control. So, Dr. Satoshi Yoshida, he was a professor, university professor for several years. He became very, very well known within the glass community for a top expert on the mechanical properties of glass. And then he decided to try another experiment. He is now the head of a big research group at AGC, a Sai glass company, a huge international glass company, and they have their a large research center in Yokohama, Japan. So Satoshi kindly agreed to give the final lecture of this day. So thank you so much, Satoshi, and please start.
Okay, thank you for all very kind introduction, Edgar. So I try to share my screen. Okay. So, right. So can you my slide?
We can see.
Can you see my slide?
We can.
Okay. Okay. So I'd like to start my talk. So my name is Satoshi Yoshida from AGC Inc. Japan. I'm very happy to join this grad school in San Carlos. I'd like to express my thanks to the organizer of this school. As Professor Zanato introduced you just before, so I'm now working in the AGC company, but 5 years ago, I changed my job from academia to the company. So today, I'd like to focus on the indentation problem in glass. Probably tomorrow you will learn about mechanical property of the glass from Professor Francisco Severna. But today I'd like to focus on indentation and hardness of the glassy materials. So this is an outline of my talk today. The first, I'd like to show you a little bit about my company, AGC Inc. Japan. After that, I show you what is a hardness. Hardness is a very, very simple mechanical property, but so complicated in amorphous system. So that I'd like to show you a little bit about hardness. After that, I show you the deformation and indentation induced cracking and fracture of the glass. So I'd like to summarize my talk. So where is the AGC in Japan? I'm now in Japan, Yokohama, Japan, and okay, and I'll show you the PowerPoint. Okay. So we have time difference of 12 hours. So I'm very, very early in the morning. So you are here in Brazil. So the AGC Inc. was established in 1907. And well, we have more than 50,000 employees in all over the world. And 180 subsidiary companies also in all over the world. So I'd like to show you a little bit about our business overview, AGC business. In 2024, the net sales is about 2,000 billion yen. It corresponds to the 13 billion US dollars. The almost 60% of the net sales coming from the glassy materials like architecture window and automotive window and displays and EUV mask blankets. The other part of our business is the chemical products. So like essential chemicals like sodium bicarbonate, and also performance chemicals means like fluorine regimes. So nowadays, life science business is growing year by year. So this is an overview of our company. So we also have the various types of the top sales products, so such as architectural glass and automotive glass, and also the cover glass for the mobile laptops and something. Now also the fluorinated resin and fluoropolymer as top sales in the world. This is a good products for the companies. So this is our brand statement, AGC Group's brand statement. So your dreams, our challenge. I like this brand statement. This AGC is always everyday essential part of our world, and we also contribute to global environmental sustainability. We are willing to challenge to realize your dream for using great products. So this is just a small introduction of our company. So that I'd like to start on the mechanical property of the glass. The first topic is the hardness of the glass. So this is a schematic illustration of the indentation test on the glass or other materials. So Baker's hardness is a very, very simple technique to measure and compare the hardness of the materials, not only glass. Now, when we use indenter, the diamond indenter, the shape is shown in the right side slide. This is a pyramid, diamond pyramid. We use this indenter on the material surface at a given load. After indentation, we can find the indentation imprint. So after that, we measure the size of the imprint and compare the size of the imprint, which is harder. The smaller imprint means harder materials, so that we can measure the size of the imprint, so now we can compare the hardness. It's a very, very simple system, simple technique to compare the hardness. So actually, so we measure the diagonal length of the imprint like this, that's shown in the left side slide. We measure the diagonal length and determine the average diagonal length as shown using this equation. And from the average length, we can also calculate the contact area at the maximum load. So using the geometries of the indenter, we can estimate the contact area using this equation. Now, Baker's hardness is defined as the load, the ratio of the load to the contact area, estimated contact area at the maximum load. So that we can use this equation to calculate the Baker's hardness of the glass and other materials. It is noted that the Baker's hardness number is obtained when the units are kilogram force and millimeter. Now, when we use the unit kilogram and millimeter, the Baker's hardness number is given without units. This is a rule, and it's a little bit complicated because hardness number is not real pressure and mean pressure, so we cannot use any units when we use Baker's hardness number. when we use the unit kilogram and millimeter. But in the scientific literature, like a paper and journal paper and something, we usually use the unit Pascal as a biggest hardness. So that in the case of the unit Newton and meter, we can determine the biggest hardness with the unit of Pascal. Pascal unit is the same unit of the pressure and something. So usually in the scientific literature, we can use the unit of Pascal. It is a little bit complicated, but sometimes we can see the biggest hardness number like 500 and 600, and sometimes we can see the hardness number, hardness value of the gigapascal, 5 to 6 gigapascal. This is the reason why the unit of the different. The first one, biggest hardness number, is the unit of kilogram and millimeter. But we can see, when we can see the Pascal unit, the biggest hardness is calculated from the Newton and meter. It's a little bit complicated system of the hardness. So this slide shows some commercial hardness of some commercial glasses. It's a silica and a BK7 and a lead silicate and transparent glass ceramics and substrate glass or liquid crystal display something. So the almost glass material, commercial glass materials, ranges from the 3 gigapascal to 8 or 9 GPa gigapascal. So I'd like to also show you some other type of the hardness number. Not only the because that we can use various types of the indenter chips and the various types of the definition of the hardness. And now I'd like to show you the three kinds of the indentation hardness. The first one is a Mayer hardness. This Mayer hardness is almost equal to the mean pressure. So the Mayer hardness defined as the ratio of the applied load to the projected surface area. For the biggest hardness, not the surface area, projected surface area, contact surface area. This is a definition of the biggest hardness. The Mayer hardness is projected surface area used. So the Mayer hardness is equal to the mean pressure. This is a little bit different from the biggest hardness. The other type of hardness is a Knoop hardness. So Knoop hardness is generally used in brittle glass system like lead glass and other optical glasses and something. So because the Knoop hardness, the tip angle of the Knoop indenter is very, very wide and large and blunter as compared with biggest indenter chips. So we can obtain the indentation impression without any cracks, even in a larger load. So we can measure the diagonal length without any crack. It's so easy to define the length, so that we can use a Knoop indenter chip for the optical glasses. The final types of the hardness is a Barkovich hardness. Barkovich indenter chip is as shown in this slide, the trigonal pyramid. The three-sided pyramid is quite sharp chip angle. So the Barkovich chip is generally used for nano indentation, very, very shallow or depth indentation test that we can use trigonal pyramids, not the biggest indenter. So the bucket chip is used to a very, very thin film and something, or the very, very small sample, we can use bucket chip. So for nano indentation system, nano indentation setup, there's a contact area is quite difficult to measure the diagonal length of something. So the contact area is estimated from the load unload displacement curve from the some equation that we can use. This is a Barkovich system. So the Maya hardness, Knoop hardness, and the Barkovich hardness is a very, very conventional hardness system for the grassy materials. So hardness is a quite simple technique, but amorphous system, this hardness is not so simple. The metallic materials, we know the Tabor's law. We know Tabor's law shows the hardness is 3 times larger than yield stress. But we cannot measure the yield stress in a glassy material. This is because the glass material is very, very brittle, so that we cannot determine the yield stress. And there's a tensile stress or the compression stress and something. So it is not work. This kind of the equation, Tabor's law does not work for the glassy materials. So the hardness of glass is not a measure of the resistance of permanent deformation. So I'd like to show you this video. This is the indentation microscope. So we can see the contact area during the indentation test. The black region is the contact area between the indenter and glass surface. In this case, the glass is a silica glass. The contact area is shown here. That we can also interference fringes around this. So this is almost maximum load. Maximum load is 3 Newton. Then after that, well, we can see the shrinkage of the contact area. This is because this is almost maximum load. Now is unloading half cycle. Now we can see the shrinkage of the contact area. This is because the glassy materials like ceramics and something, so very, very elastic property. Then plastic material shows a large elastic recovery during the unloading half cycle. So I'd like to say the hardness is not the resistance to plastic deformation, but the plastic deformation, resistance to the elastic. Okay. So using the such kind of indentation microscope, we can plot these types of the load and area relationship, not to the depth. So normally there's a nano indentation system that we can obtain the load and depth relationship. But using such kind of the microscope, that we can determine the contact area during the indentation. So we can plot the indentation load against the contact area. During the loading half cycle, that's a red point here. From this slope of the curve, we can determine the hardness. And loading half cycle, the blue point, from these data that we can estimate the elastic modulus, Young's modulus, something. So this is a direct relationship from the using this kind of contact area that we can see the elastic modulus and the hardness. The hardness is not the resistance of plastic deformation. This is elastic plastic deformation. This is including elastic deformation, not only the plastic deformation. This is my message in this lecture. So this is the snapshot at the maximum load in the left side slide here. The right side photo shows indentation imprint after complete unloaded. The size is quite different. This is due to elastic recovery. So we can measure the diagonal length after complete unload and estimate the contact area at the maximum load. This is quite different. So I'd like to say the hardness of glass and the hardness ceramics is a measure of the resistance to plastic deformation, not the plastic deformation. So how can I do? There's not only the hardness, we focus on the hardness and the elastic modulus. So this slide shows the relationship both in parameter and H over E is the elastic modulus, HM is a Mayer hardness. So the H over E is a quite important mechanical parameter of the glass and ceramics. So bonding parameters, as shown in the left side figure, that a bonding parameter is a ratio of the diagonal length to the face-to-face distance. So the larger bonding parameter shows a larger recovery during the unloading half cycle. So this is one kind of elastic parameter, elasticity index. So with increasing the H over E of the materials, this means there's an elasticity, high amount of the elastic part of the deformation is dominant and is indented. So this plot is various types of the glassy composition. So with increasing the H over E hardness to elastic modulus, so the bonding parameter and also increases. So the elastic index is also, we can help to compare the elasticity in various types of the glass systems. So the hardness glass is very, very simple, so that we can measure the hardness using the indentation, diamond indented chips. Now, from the size of the imprint, we can measure the hardness. The biggest hardness of commercial glass is falling in the range from 3 to 8 GPa. The hardness of glass is a measure of resistance to elastoplastic deformation, not the plastic deformation. I'd like to say the hardness is generally taken as a resistance to plastic deformation. That's not true. There's a hardness glass is resistance to elastic plastic deformation. So what we should use H over E parameter. This is one kind of the measure of the elasticity of the materials, ceramics and glassy materials. So due to the limited time in this lecture, we do not talk about the indentation size effect. It is also important. So depending on the load, indentation load, that we can find different hardness number, even in the same identical material. This is important, but please check the other literature something. Okay. So next topic is deformation and fracture, cracking in the glass. So we know that if we increase indentation load, we can find the cracking and fracture around the indentation imprint. As shown in this slide, the left side shows the imprint obtained at the load of 0.1 Newton. It's a very, very smooth indentation imprint, surface of the imprint. But we increase in load, like 5 Newton, 500 gram force. So we can see such kind of radial crack from the corner of the indents. So the indentation induced cracking should be affected by elastic deformation and plastic deformation. So I'd like to talk about what is controlling this kind of the cracking in glass. So as shown in the previous slide, I showed that during the indentation cycle, that we can find various types of the deformation mode. The first one, elastic deformation. We can see the large elastic recovery using indentation microscope, something. And after indentation test, we can see the plastic deformation, the indentation permanent imprint. So it is interesting. There's an amorphous system like an oxide glass and something. We can find the two types of the permanent deformation in glass. One is densification. Densification means increase in density. The frozen state of the high density state is stable for the glasses system. This is a very, very characteristic mechanical property of the amorphous system. The first one is densification. The other one is shear flow. This is like other crystalline materials, like thanks to the dislocation or something. This also occurs in a glasses system. Now, finally, the other important phenomenon is a fracture. Increase in the indentation load. Now we can see the cracking, radial cracking and something. So these phenomena is a very, very complicated mixture during the indentation test. Today, I do not talk about temperature or something. Temperature or pressure also affect hardness and other indentation property of the glass. The first one is cracking from the elastic deformation, elastic property. Top two photo shows a snapshot during the indentation using an indentation microscope or the silica. So during the loading half cycle, we can see the ring crack. This is a shadow of the ring cracks. And sometimes we can see edge crack, and also on the cone crack, we can also see this photo. For soldering glass, we cannot see any cracks during the loading half cycle. But during the unloading half cycle, we can see this edge crack, and finally we can see the radial crack from the corner. So quite different. So now depending on the glass system, depending on the glass composition, we can see different cracking behavior, even under the same loading condition. This is important. So depending on the composition, the indentation fracture is quite different among the glass composition. So it is well known that crack nucleation, crack initiation load for radial crack depends on the glass composition. So this slide shows very, very old data in 1974. This is one example of the compositional variation of the indentation cracking among various glass composition. The vertical axis shows the crack forming probability, the 100%, from 0% to 100%. The 100% probability means imprint. The four corners of the biggest imprint every corner has a crack. The four cracks that we can see. like this photo. The 50% crack probability means that two cracks have to, this imprint have the two cracks from the two cone. Other two have no cracks. This is the vertical axis. The horizontal axis shows the indentation load from 20 gram force and 2,000 gram force, 2 kilogram force and something. So depending on glass composition, these are some commercial glasses that we can say the mother glass of bicoal type of glass are very, very strong and even under the 500 gram force indentation, we cannot see any crack around the indentation imprint. But lead glass and or Windows solar glass, there's only the 20 gram force, 30 gram force that we can see the radial crack around the indentation imprint. This is a quite big compositional variation for the indentation cracking system. So the other example is Setsuro Ito from Asahi, and this work is 1998. It's old data. It's about important one. There's a vertical axis shows also the probability of cracking, and the horizontal axis shows the indentation load. This plot shows cracking behavior of two types of soda-lime glass. The one is conventional soda-lime glass. The other one is less brittle. A little bit change of the composition, resulting in a very, very big change of the cracking behavior. We cannot see any crack at the same indentation load, 1 kilogram force. There's a cracking behavior. The less brittle glass shows 10 times larger cracking behavior. The composition has not so big change, a little bit larger in silica and smaller amount of calcium. This is quite improved the cracking behavior for the soda-lime silica system. So the cracking behavior is very, very sensitive to glass composition. So the question now we have is what controls the cracking, indentation cracking behavior? So in order to understand that, this slide shows the relationship, the crack initiation load, indentation crack initiation load, and Baker's hardness, the left side, and the fracture toughness in the right side. So some glass composition is plotted in this graph. So we can say almost no relation between the crack initiation load and the hardness, Baker's hardness, and the fracture toughness. So that we cannot use any conventional mechanical property to compare to understand the indentation cracking behavior. So we should focus on the other property of the glassy material. So what controls the indentation cracking? So the answer is the deformation mechanism of glass system. As shown in the previous slide, the amorphous system, like the oxide glass, shows the two types of the deformation mechanism under the indentation. The first one is shear flow. If we use sharp indenter means tip angle is smaller as compared to the Baker's indenter chip. So we use such kind of sharp indenter that we can see very, very distinct pileup around the indentation imprint, like metallic materials. This is a very, very large pileup. So this is evidence of the shear flow. This is soda-lime glass, not the metallic materials. This is a soda-lime glass. This is the one kind of deformation mechanism. The other types of the mechanism is densification, permanent densification. The glass material shows a frozen state with higher density. This is a cross-section view of the border indentation imprint. This is the after indentation. We can see the cross-section view. We can also see the black region. Black region represent the changing refractive index. Changing refractive index correspond to changing density. This also happened in densification, permanent densification. This is also soda lime glass. So dependent on the indented geometries, that we can find different types of the deformation mechanism, densification and shear flow. So this is also the case for the glass composition. Depending on the glass composition, we can find different amount of the shear flow and a different amount of densification occurs under the indentation. So in order to understand the driving force for cracking, I'd like to show you a little bit very, very simple equation, simple relationship. Showing the left side this slide, this is a simple relationship, the stress and the strain. Stress and strain is equal to using the connected to using bulk modulus. In this case, there's a volume strain. Volume strain times bulk modulus is equal to stress. This is the residual stress after indentation. Now, what is the volume strain? So in order to imagine the volume strain around the indentation imprint, as shown in the right side figure, first we can imagine the partial deformation zone. So before indentation, we can imagine first in a partial deformation zone. So during indentation, we can create indentation impression. After indentation, the indentation leaves impression. In general, so deformation, permanent deformation, is volume conservative. So the deformation at the loss of volume is result in the expansion of the deformation zone. But in reality, this region cannot expand due to the constraint around the elastic region around the deformation zone, that this region cannot expand. So this is a result in the tensile stress. This is the reason why the indentation system, indentation test, causes cracking around the indentation imprint. This is the mechanism of the indentation induced cracking. So our glass system, as shown in the previous slide, so glass shows two different deformation mechanisms. One is shear flow and the other is densification. The shear flow means an expansion of plastic flow, but densification do not expand the volume. This is because densification means a change in density, increase in density. So this is the shrinkage, no expansion. So dependent on the deformation mechanism, the volume strain is quite different among the glass composition. So in order to estimate, very, very simple technique to estimate the amount of densification around the indentation imprint, I employed an annealing technique. The first, I impressed the indentation test, that we can see such kind of indentation imprint. After kneading, we can see shrinkage of the imprint. This is due to the relaxation of the densified state to the initial state. So the volume is expanded due to annealing procedure. So the densification contribution, volume contribution, is defined as the densified volume, recovered volume after annealing, and to the initial volume. This is the volume ratio of the densification. We call it the percent densification. So this slide shows some relationship of the percent densification volume ratio of the densification to the Poisson ratio. So with increase in the Poisson ratio or the decrease in the Poisson ratio, the percent densification is increasing. The contribution of the densification increase with decrease in the Poisson ratio. The Poisson ratio, decrease in Poisson ratio means the increase in the free volume and the atomic scale. So the free volume changing the under the pressure and something that we can obtain the high density state of the glass. So the lower Poisson ratio, so increase in the Poisson densification. And it is not that Poisson ratio is the elastic parameter, not a plastic one. So this is interesting, and this is a characteristic property of the glass. The permanent deformation in glass system is one kind of the frozen state of elastic state. So this is relationship, Poisson ratio and Poisson densification is quite characteristic for the amorphous system. This is a very, very interesting relationship. So I'd like to go back to the indentation cracking system, the very, very wide compositional variation of the indentation cracking. So the right side figure shows the relationship crack resistance and indentation crack resistance and percent densification. So with increase in the percent densification, the contribution of densification, the crack resistance is also increasing. This is a one case, not the conventional one as a permanent one, but the one parameter of the percent densification controls indentation-induced cracking. So this is just an estimation method of the amount of densification. So we'd like to know how to measure quantitatively the residual stress around the indentation imprint and compare, we'd like to compare the residual stress among the different types of the glass system. So in order to do that, we employed integrated photoelasticity. Photoelasticity is a very, very old technique to estimate, to determine the residual stress and the residual strain in the glassy products. So we'd like to know the elastic residual stress around the indentation imprint. So using the polarized light and the analyzer, we can obtain the retardation and azimuth slow axis orientation direction at each pixels. From these values, we can estimate, we can determine the stress field around the indentation imprint. In order to do that, we use a conical imprints, not the Vickers and Barkovich and something. So because the stress field created by the conical indenture is an axis symmetrical stress field, so that we can estimate the three-dimensional stress field around the indentation imprint. So this slide shows a result of the integrated photoelasticity as shown in the right side figure. The left side shows calculated stress using the Helmholtz equation. The red region is tensile stress region and blue region and compressive one. The black line shows the direction of the principal stress. So the left side is calculate one, and the right side is experimental photoelastic stress field. So these included various experimental errors, but these are acceptable, reasonable, and almost similar to each other. So the integrated photoelasticity is one kind of estimate of the residual stress or stress-induced indentation. This is an insight to determination of the stress field. But this technique, we can apply this technique to the residual stress also. So this is the result of the residual stress of the two kind of silicate glass. The left side shows silica, the right side shows sodium silicate. In this case, also the red region is tensile 1, but this is not the principal stress. This is a radial stress. So this region is a tensile 1. For silica, the tensile region is located at the surface. This is after indentation. This is the residual stress field. For silica, the tensile stress region is located on the surface. But sodium silicate, the tensile region is the bottom of the deformation region. Bottom of the deformation region means that this is the origin of fracture for the radial crack. Actually, so when we increase the indentation load 7.5 and 4.0, then we can see the different types of cracks. The silica, there's a ring crack, we can see for sodium silicate, that we can see radial crack. This is due to the different stress field for the tensile region is different depending on the glass composition. So this is the important result. So the such kind of different stress field result in the different cracking behavior in the glass. So finally, I'd like to show the effect of contact speed on the deformation and cracking behavior in glass. So in order to do that, we prepared two kind of indentation microscope. The first one is quasi-static test. This is a normal universal tester attached with indenter chip. In this case, the indenter chip is a Barkovich chip. So during the indentation system, we can observe the indentation contact lesion using the high-speed camera. The right side shows this is a dynamic indentation microscope indentation test. When we use frictionless stage, we can obtain higher impact velocity. For example, just a 10,000 millimeter per minute. So during the indentation system, we can see the contact region during the test. So we can see the left side shows quasi-static indentation test. Using a Barkovich chip, the trigonal pyramid indenter, so that we can see the three types of radial crack during the unloading half cycle. The right side video shows a dynamic indentation test. In this case, now we can see a very big chipping, and also the cracking is happening during the loading half cycle. So in order to see that, I'd like to show you the relationship between the load and time. The maximum load is almost same, 300 Newton, but the contact duration time is quite different. For quasi-static indentation, the contact duration time is 40 seconds. For the dynamic test, only 1.5 millisecond. It's a quite small contact, short time, during the indentation. The arrows shows this is a serration mark correspond to the cracking. So I'd like to say that during the dynamic indentation test, we can find so many cracking during loading half cycle. So for the quasi-static indentation test, that's only one step during the loading system. This is a quite different cracking behavior depending on the contact speed. So this slide shows summarized cracking behavior depending on contact speed. For the quasi-static indentation, the crack initiation load is larger as compared with dynamic indentation. So the crack types also different. The static test that we can find a very long radial cracks for the dynamic test. Chipping and edge cracks are dominant. And the cross-static test, the cracks happens during the unloading half cycle, but dynamic test that we can see the cracking during the loading half cycle. So I'd like to say the contact speed is also affect the deformation mechanism and result in the cracking behavior. So this slide shows optical micrograph of the indentation imprints. The left side shows a static indentation imprint. The right side shows a dynamic indentation imprint. In order to see the clear image, that we use blunt trigonal pyramid indentation. So this chip angle is very blunter as compared with Barkovich chip, so that we can see the indentation imprint without severe cracks. For the static test, quasi-static test, we can see many shear lines around the imprint, but we cannot see any shear line for the dynamic indentation test. So I'd like to say the deformation mechanism is different depending on contact speed. The bottom two image shows a photoelastic retardation map of the indentation imprint. The red region shows higher retardation, and the black and blue region is a lower retardation region. So that we can see the higher retardation around the shear line, and this also maybe the some driving force for cracking and something. So depending on contact speed, plastic deformation or shear flow is dominant for the slower indentation. For the faster indentation, the densification or elastic deformation is dominant for the during the indentation. Okay, this is the final slide of my lecture today. So thank you for listening. The first one is the hardness of glass is a measure of resistance to elastoplastic deformation, not to only plastic deformation. This is because that we should compare H over E parameter among the various glass composition. So not only the hardness, we can compare the elasticity or plasticity among the glass composition. This is important because the plasticity or elasticity controls the cracking behavior of the glass. The second point is densification reduce the residual stress during the indentation test, or the hardness test, or scratch test, and something. The third point is lower Poisson ratio resulting higher Poisson densification and less radial crack. The fourth point, because of rate-dependent deformation, this contact speed also affects the cracking deformation behavior and cracking behavior in glass. the quasi-static indentation prefer a shear flow and a dynamic test go to permanent densification. So we should know much more about shear flow. Well, I talk about densification. I talk about the permanent densification is a quite important parameter among the glass system, but we do not so much about shear flow in the glass. But shear flow is quite important and a quite key parameter controlling the cracking behavior. So the shear flow may change atomic structure and chemistry and property and something. So that we should know much about the shear flow in the glass. Okay, so thank you so much for your kind attention. That any question, even after school, your questions are welcome. Please send an email and please send an email to Professor Zanotto and something. So I hope to see you anywhere in coming conference and something. So thank you again. Thank you so much.
Thank you very much, dear Satoshi, for your brilliant lecture. This is a real lecture, a nice, very nice overview, you know, all about you want to know. I'm sure it's not all about, but a lot about indentation. I'm sure there are many questions. Let me start with one before I forget. I'm tending to forget things, you know, with age. Satoshi, it's known or it's advertised that humidity plays a role, affects measurement of hardness. Now, it's well known that humidity has a large effect on crack propagation, stress corrosion cracking, blah, blah, blah. This is well known. However, I fail to understand why it affects indentation before. I'm talking about before crack propagation. Indentation with small loads, before you have any cracks. Why the humidity affects the measurement of hardness?
Oh. So as you say, the crack propagation or crack initiation is very, very sensitive to humidity around the, depending on the relative humidity. There's a cracking behavior is quite different. There's a hardness number. Hardness number is also affected by humidity. This is because Professor Tomozawa knows well under the high humidity, during the indentation, the water is diffused into the deformed region. So the hardness is decreased during the indentation. Maybe there's a very, very dynamic, there's a kinetical point of view, so the water is penetrate under the indenter during the indentation system. This is one reason to control humidity. There's a change in the humidity controls hardness. And yes. Now also there's not only the penetration at some, it is also the hardness is very, very complicated. There's not only the deformation, there's some very, very small fracture is also occurs under the indenter. So the under the very, very high humidity, such kind of bond breakage is also assisted under the water molecule and something. This is my impression, but not clear at the present stage, I think.
Thank you. Thank you. I understood. I'm going to give the microphone to Francisco Serbena now.
Okay.
Hi, Satoshi. Thank you for your...
Hi, thank you.
Hi. Thank you for your nice talk. I wonder if the factors that control, crack propagation is controlled by E over H and densification. the ratio between densification and shear flow. Yes? What factors do you think would control crack nucleation? Because we see in the plots this crack resistance for different type of glass. Edgar already mentioned the problem of humidity, but apart from humidity, fatigue effects, what factors do you think would control? Of course, densification is one, but K1C or the ratio K1C over hardness or whatever. What do you think about?
Okay. So the one is E over H, as you say. The E over H is controlling this kind of the nucleation behavior, because E over H is closely related to the driving force for the cracking, as you know. So larger E over H means the plasticity of the glassy material against the indentation. So larger E over H means larger residual stress for radial cracking. So even under identical loading condition, dependent on the E over H, the residual stress increase. So the driving force for cracking is one factor for the indentation cracking behavior. So the other factor is densification, I think. Densification is the when we imagine the same number of knobs, biggest hardness, but different amount of the densification contribution. Hardness is the same, and E over H is also same, but different amount of the densification. In that case, the densification also controls the indentation crackiness. So the one is E over H parameter, the other is the densification contribution, I think. But not the case, not only the case. As you say, there's a humidity and other temperature also, and surface condition. Surface polish condition is also very, very sensitive to the indentation cracking, I think.
Okay, thank you.
Thank you for question.
Any other questions? Two ladies here.
Okay. Hello, Mr. Yoshida. My name is Shirin. I'm from Shisejam, and I have a question for you about something different, maybe. So when we are producing glass bottles at the plant, these bottles go through different types of mechanical tests, like internal pressure or burst, you know. So if I want to design a new composition for a glass bottle, I will not have a readily available glass bottle with this new composition, but I will have a bulk glass. So which mechanical property should I try to improve, or should I try to analyze, and which can be correlated to the test that we do in the plants? What do you think about that?
It's a glass bottle. The internal pressure and something. I think it's the most important is the surface condition. Though I'm not so sure, but maybe there's a surface treatment or something. I'm not sure. There's something that's the surface treatment and surface modification, and something as almost there's a primary important of the surface condition. So the mechanical property is just the averaged one. Hardness and also as elastic modulus. Also, the important point is fracture occurs at the very, very weakest point. So the weakest point and is maybe the surface. So the surface is controlled. If you compare the strengths of the old composition and new composition. So in order to compare the strengths and how improve the strengths and something, so you prepare the surface, the same surface, identical surface, and it's quite difficult, but the surface is quite important, I think. So I'm not sure that's a good answer, but just a comment on this question.
Thank you very much.
Hello, Dr. Yoshida. Thank you for such an informative presentation. It is just an overview of the mechanical properties. So I just have a couple of questions, very basic, I just wanted to understand. So when you showed the crack resistant plots, I can see that after getting the crack resistance values, you have fitted it with a sigmoidal curve in order to finally find out the load at 50% crack initiation probability. So I just wanted to ask you, like, what is the function which we should be using in order to fit the data? If it is sigmoidal, why are we using sigmoidal function? And I have also tried to measure the crack resistance values for some of my glasses, and the scatter of the data is not perfectly fitting to sigmoidal curve. So in that case, what should be the function which we should be using in order to finally find the load at 50% crack initiation probability? So this is my first question. I think after you answer, I'll go ahead with my second question.
Okay, thank you for your question. So this S-type curve, normally we are plotting using this curve, the sigmoidal curve, as you say. So sigmoidal curve plot and determine the load at 50% cracking probability. It is no problem. But the mechanism, this S-type curve, is maybe coming from the Weibull relationship, so that we can also plot the Weibull statics also. This is a very including various types of experimental errors, so that we can also fit in using the sigmoidal curve, also fit in with Weibull statics, and also, I don't know, there's a very different types of the curve. So the mechanism is surface crack, surface flows. Depending on the surface flows, we have the very sharp increase in this curve, but sometimes a very narrow shapeness S-type. This is due to the surface condition. So this is coming from the amount of the size of the flow, the amount of the different lengths of the crack on the surface is controlling the shape of the S-curve and the sigmoidal curve, I think. So that some people, they're fitting this plot using the Weibull statics. I also tried it, and this is a one solution. But due to the very large scattering, there's the other types of the fitting curve is also acceptable, I think.
I apologize. I have to thank you so much, Satoshi. The technicians have a contract. They have to leave now. We have to go out, and they have to close the offices 6:30.
Yes.
So thank you very much. Please send Dr. Yoshida your questions by email. He'll be most happy to answer.
Okay.
Thank you so much, Satoshi.
Thank you.
Carolina.
Thank you. See you.
See you somewhere.
Yes.
Bye.
Hi guys, I'm Anna here. So I'm going to the bar now. If you want to join with me, you can go together. And as I sent in the WhatsApp group, for those who going later, going to the bar by 7:30 because we have live music tonight. So thank you.
Acho que eles foram se trocar, coisa. Já falou tudo certinho? Então vai quanto? Vai